Look up at the night sky. What you see, the pinpricks of light from distant stars, the faint smear of a neighboring galaxy, is only a tiny fraction of what is truly there. For every shimmering galaxy, every brilliant star we can observe, there is an immense, unseen presence holding it all together. This is the cosmos's best-kept secret, a vast, intricate architecture woven through the emptiness of space, an invisible scaffold upon which the entire visible universe is built. We call this the cosmic dark matter web, and it is one of the most profound and baffling concepts in all of science. It's a structure so grand it defies our everyday understanding, a hidden framework that dictates the fate of galaxies, yet it remains completely imperceptible to our eyes and our finest telescopes. This isn't science fiction. This is the leading edge of our understanding of reality, a shadow universe existing in parallel to our own, and its discovery has fundamentally rewritten the story of our cosmos. For centuries, we have mapped the heavens by the light they emit, but we are now realizing we have only been reading the footnotes of a much greater text. The true narrative of the universe is written in the dark. The very fact that galaxies spin at speeds that should tear them apart, that colossal clusters of galaxies move with a gravitational pull far greater than their visible mass can account for, points to a single, inescapable conclusion. Something massive is out there, exerting its influence on everything we see. This something is dark matter, and it forms a web-like structure of filaments and nodes that stretches across billions of light years. This cosmic web is the true backbone of the universe, the hidden skeleton that gives the cosmos its shape and form. To comprehend it is to take a step closer to understanding the most fundamental laws governing existence itself, from the birth of the first galaxies to the ultimate fate of all we survey. In this journey, we will venture into the heart of this magnificent mystery. We are going to explore 25 of the most compelling, puzzling, and awe-inspiring questions that scientists are grappling with today. We will ask what this dark matter web is truly made of, how it first formed in the fiery aftermath of the Big Bang, and how it guides the evolution of galaxies. We will confront the possibility that we might be searching for not one, but several different kinds of invisible substances. We will even question if dark matter itself might be a sign that our theories of gravity are incomplete. This is not a story with easy answers, but one of ongoing discovery, where each new observation peels back another layer of the cosmic onion, revealing ever deeper levels of wonder. So prepare to look at the universe in a completely new way, to see the empty spaces not as voids, but as the most important parts of the picture. The journey into the dark is about to begin. Our journey into the shadows begins with a fundamental and almost unsettling question. How can we be so certain that something exists when we cannot see it, touch it, or directly detect it in any way? The answer lies not in the darkness itself, but in the way visible matter behaves within its invisible grip. The story of dark matter's discovery is a classic scientific detective story, where the evidence was a series of anomalies, clues that the universe was not playing by the rules we thought we understood. The first major clue emerged from the careful study of galaxies, specifically how the stars within them orbit the galactic center. According to the laws of gravity as defined by Newton and Einstein, stars on the outer edges of a spiral galaxy, far from the central bulge of mass, should move much more slowly than those closer in. Think of our own solar system. Pluto, way out on the fringe, orbits the Sun at a sluggish pace compared to Mercury, which zips around at a tremendous speed. Astronomers expected to see the same pattern in galaxies, but in the 1970s, an astronomer named Vera Rubin, along with her colleague Kent Ford, decided to put this assumption to the test. They meticulously measured the rotation speeds of stars in the Andromeda galaxy, and what they found was astonishing. The stars on the outskirts were not moving slowly at all. They were orbiting just as fast as the stars near the center. This was like discovering that Pluto was racing around the Sun as quickly as Mercury. The only way this could be possible is if there was far more mass in the galaxy than what was visible, a huge halo of invisible matter providing the extra gravitational pull to keep those outer stars from flying off into intergalactic space. This phenomenon, known as the galaxy rotation problem, was our first solid indication that the universe was filled with something we couldn't see. Around the same time, observations of giant clusters of galaxies provided another, even more dramatic piece of evidence. These clusters contain hundreds or even thousands of galaxies, all bound together by gravity. Scientists calculated the total mass of all the visible stars, gas, and dust in these clusters and found that it was nowhere near enough to generate the immense gravitational forces they were observing. There had to be something else, a hidden source of mass accounting for the vast majority of the cluster's weight. The most stunning proof came from a phenomenon predicted by Einstein's theory of general relativity, gravitational lensing. Massive objects warp the fabric of space-time around them, bending the path of light that passes nearby, acting like a cosmic magnifying glass. When astronomers looked at these galaxy clusters, they saw the light from distant galaxies behind them being stretched and distorted into faint, smeared arcs. The amount of bending was far too extreme to be caused by the visible matter alone. It was as if they were looking at a magnifying glass made mostly of invisible glass, with only a few specks of dust to hint at its true, massive shape. These independent lines of evidence, from spinning galaxies to bending light, all pointed to the same incredible conclusion. The matter that makes up everything we can see, every planet, every star, every galaxy, accounts for less than 5% of the total content of the universe. The current consensus, based on painstaking measurements of the cosmic microwave background radiation, the afterglow of the Big Bang, tells us that dark matter makes up about 27% of the cosmos. That means for every single particle of the familiar atoms that build our world, there is more than 5 times as much dark matter out there, an unseen ocean in which the islands of visible galaxies float. This invisible framework is not a minor component. It is the dominant architectural material of the universe, the hidden scaffolding upon which the entire cosmic structure is built. So, we've established that this invisible substance must exist, but that immediately raises an even more profound puzzle. If it's not made of the same protons, neutrons, and electrons that constitute you, me, and every star we see, then what in the universe is it actually made of? This is our second great mystery, the fundamental identity of dark matter. Scientists have been searching for the answer for decades, and while we haven't found the smoking gun, we have some very compelling suspects. The leading candidates are particles that belong to a realm of physics far beyond the Standard Model, which is our current catalogue of known particles and forces. These hypothetical particles are strange, elusive, and would have properties that seem almost magical to us. The most famous candidate for many years has been the WIMP, which stands for Weakly Interacting Massive Particle. The name itself tells you a lot about its proposed nature. Massive means it has a significant weight, perhaps dozens or even hundreds of times heavier than a proton. This heft is necessary to provide the gravitational pull we observe. Weakly interacting is the crucial part. It means these particles barely talk to normal matter. They don't feel the electromagnetic force, so light simply passes right through them. They don't feel the strong nuclear force that holds atomic nuclei together. Their only way of interacting with our world, aside from gravity, would be through the weak nuclear force, which is responsible for certain types of radioactive decay. This extreme shyness is precisely why WIMP have remained hidden. They would flood the room you're in right now, passing through your body and the Earth itself as if they weren't even there. For years, WIMP were the favorite because theories suggested the right number of them would have been created naturally in the hot, dense early universe, perfectly matching the amount of dark matter we detect today. However, despite incredibly sensitive experiments deep underground designed to catch the incredibly rare bump of a WIMP hitting a normal atom, we have yet to find definitive evidence. Another intriguing candidate is much lighter and stranger, the axion. Imagine a particle that is billions of times lighter than an electron, almost like a ghostly wisp of a particle. Axions were originally proposed to solve a completely different, esoteric problem in particle physics concerning the symmetry of forces, but they turned out to be a perfect dark matter candidate. Because they are so incredibly light, axions would behave less like discrete particles and more like a pervasive, invisible energy field that fills the cosmos. If dark matter is made of axions, it would be a kind of cosmic fluid sloshing and waving through space. Detecting an axion is a monumental challenge, requiring powerful magnetic fields to potentially convert them into faint photons we can see. The search for axions is like trying to hear the faintest possible whisper in the middle of a roaring hurricane. Then there are the possibilities that lie within extensions of what we already know, like sterile neutrinos. We are familiar with regular neutrinos, the elusive particles that stream from the sun and nuclear reactions, barely interacting with anything. The problem is, regular neutrinos are too fast and light to be the main dark matter. They zip through the universe at nearly the speed of light and are dubbed hot dark matter. A sterile neutrino, however, would be a heavier, slower cousin that doesn't even interact via the weak force, making it even more detached from our reality. Its presence might only be betrayed by occasional decays that produce faint, specific X-rays that astronomers could potentially detect. This brings us to a key point. Why can't familiar particles like regular neutrinos be the answer? The structure of the cosmic web itself gives us the clue. The dark matter web we see is clumpy with dense nodes and filaments. For gravity to pull matter together into such a precise scaffold, the dark matter particles must be moving relatively slowly, what we call cold dark matter. If the dominant dark matter were hot and fast-moving like regular neutrinos, its particles would have streamed freely across the early universe, smoothing out those nascent clumps and preventing galaxies from forming until much later. The universe we observe, with its intricate web of galaxies, tells us that whatever dark matter is, it must be predominantly cold and slow-moving. Each of these candidates would sculpt the cosmic web in a subtly different way. A universe built on heavy WIMP might have a more granular, chunky web structure. A universe filled with ultralight axions could exhibit wave-like phenomena on vast scales, perhaps creating fuzzy filaments. The precise arrangement of galaxies we map out with our telescopes is therefore not just a pretty picture. It is a fossil record that holds clues to the very identity of the invisible material that carved it. Our search for dark matter is a double hunt, happening both in deep underground labs and in the deepest reaches of space, as we try to match the ghostly fingerprints left on the cosmos to the particle that made them. But if dark matter forms this vast cosmic scaffold, then where are all the buildings? That's the essence of our third great mystery, a puzzle that arises when we compare our sophisticated computer simulations of the dark matter web with the actual universe we see through our telescopes. These simulations are like cosmic laboratories. Scientists program in the known laws of physics, including the gravitational influence of dark matter, and then press play, watching as billions of years of cosmic evolution unfold in a matter of weeks. The results are breathtakingly beautiful, generating intricate web-like structures that uncannily resemble the large-scale distribution of galaxies we observe. But when we zoom in on a galaxy like our own Milky Way in these simulations, something peculiar emerges. The model predicts that our galaxy should be surrounded by a vast swarm of thousands of smaller dark matter clumps or halos. Each of these halos is a gravitational pit, a potential site for a small galaxy to form. According to the simulations, the Milky Way should be the central hub of a bustling metropolis of dwarf galaxies. Yet, when we count the actual dwarf galaxies orbiting our home, we only find a few dozen. This glaring mismatch between prediction and observation is known as the missing satellites problem. It's as if our blueprint for the universe calls for a sprawling suburb, but when we look outside, we see only a handful of houses. This isn't just a minor accounting error. It strikes at the heart of our understanding of how galaxies coalesce within the dark matter web. So, what happened to all those missing halos? Scientists have proposed several fascinating solutions. One possibility is that the halos are there, but they are dark. The vast majority of these small dark matter clumps may never have managed to pull in enough gas to ignite star formation. They would be completely invisible to our telescopes, ghost galaxies made almost entirely of dark matter, drifting silently through the cosmic night. The gravitational pull from these dark halos could still be detected through subtle effects, and astronomers are actively searching for these signatures. Another compelling idea is that our detection methods simply aren't good enough yet. Finding faint, diffuse dwarf galaxies is incredibly challenging. They have very few stars spread over a large area of sky, making their light exceedingly difficult to distinguish from the background glow of the universe. It's like trying to spot a handful of faint fireflies against a brightly lit city skyline. New, more powerful telescopes with incredibly sensitive cameras are beginning to peer deeper into the halo of the Milky Way, and with each new survey, they are indeed discovering more of these ultra-faint dwarfs. However, the numbers are still far short of the thousands predicted. This suggests that while better technology will help, it may not solve the entire puzzle. This leads to a more profound explanation that involves the very nature of galaxy formation. The early universe was a violent place, filled with intense radiation from the first stars and galaxies. This radiation, particularly the harsh ultraviolet light from massive stars, could have heated the hydrogen gas throughout the cosmos, making it too energetic to collapse into the smallest dark matter halos. Essentially, the environment may have been too hostile for baby galaxies to be born in the smallest gravitational nurseries. Only the larger, more massive halos had a strong enough grip to overcome this heating and successfully form stars. This process, called reionization feedback, could have effectively sterilized the smallest halos, leaving them dark and starless. The missing satellites problem, therefore, isn't just about counting galaxies. It's a crucial test of our models for the complex interplay between dark matter and the ordinary matter that lights up the sky. By studying this discrepancy, we are learning that the cosmic web isn't a static sculpture. It's a dynamic arena where gravity, radiation, and the flow of gas engage in a delicate cosmic dance, a dance that ultimately determines which pieces of the dark scaffolding will ever shine with the light of stars. This brings us to a mystery that strikes at the very equations we use to model the dark universe, a puzzle centered on the hearts of galaxies themselves. Computer simulations of dark matter have been extraordinarily successful on the largest scales, but when we zoom into the inner sanctums of individual galaxies, a troubling discrepancy emerges. The models predict that dark matter should be densely packed towards the center, forming a sharp peak or cusp of incredible density. Imagine a steep, mountainous hill where the concentration of dark matter grows rapidly as you approach the very core of a galaxy. This is what our most fundamental understanding of how cold dark matter behaves under gravity tells us should happen. However, when astronomers study the motions of stars and gas within real galaxies, particularly small, faint dwarf galaxies, they often find something very different. Instead of that predicted dense mountain peak, the data suggests a much gentler profile, more like a flat-topped hill or even a central plateau, what scientists call a core. The stars in these galaxies seem to be orbiting as if the dark matter in the center is distributed more smoothly and evenly, lacking that intense central concentration. This conflict between the simulated cusp and the observed core is the great core cusp problem, and it has been a persistent thorn in the side of cosmology for decades. Dwarf galaxies are the perfect laboratories for testing this because they are dominated by dark matter. The confusing effects of vast numbers of bright stars and complex magnetic fields are minimized, allowing us to see the gravitational influence of dark matter more clearly. So, what could be causing this mismatch? Scientists are exploring two broad, fascinating possibilities. The first is that there might be something inherently wrong with our assumptions about dark matter itself. Perhaps dark matter particles have properties we haven't yet accounted for that prevent them from clumping too densely. For instance, if dark matter particles could interact with each other through some unknown force, a kind of dark photon, they might collide and scatter, generating a pressure that smooths out the central cusp into a core. It's analogous to how gas particles in a balloon exert pressure to maintain an even distribution. Alternatively, if dark matter were extremely light, like axions, it could exhibit quantum mechanical wave-like behavior on galactic scales, which might naturally prevent the formation of ultra-dense central peaks. The second, and perhaps more promising, explanation doesn't require changing dark matter at all, but rather demands a deeper appreciation for the complex role of normal matter. This is where the concept of baryonic physics comes in, the physics of the protons, neutrons, and electrons that make up stars, gas, and us. For a long time, simulations focused purely on the gravitational dance of dark matter, treating ordinary matter as a passive bystander. But we now know that ordinary matter is anything but passive. It can fight back against gravity with tremendous force. The key mechanism is thought to be stellar feedback, particularly from supernova or the catastrophic explosions of massive stars. In the early life of a galaxy, waves of star formation would have created generations of these brilliant, violent explosions. The energy released from countless supernova would have acted like a cosmic blowtorch, heating the surrounding gas and driving powerful winds that push material out of the galactic center. As this normal matter is violently ejected, the gravitational potential at the galaxy's core suddenly becomes shallower. Since dark matter is responsive to gravity, the sudden loss of this central mass causes the dark matter particles to respond by moving outward, effectively relaxing into a broader, smoother distribution. Think of it like a seesaw. If you have a heavy weight in the center and you suddenly remove it, the entire balance shifts. The dark matter sloshes outwards, transforming the predicted dense cusp into the observed flat core. This process is a testament to the fact that the universe is not a simple, gravity-only system. It's a complex feedback loop where the explosive lives and deaths of stars can literally reshape the invisible scaffolding of reality itself. The core cusp problem, therefore, is not necessarily a failure of the dark matter model, but a powerful reminder that to understand the dark, we must also fully understand the light. Building on the puzzle of missing galactic satellites, we encounter an even more specific and telling challenge known as the too big to fail problem. This mystery focuses not on the countless small, faint halos that might have failed to form stars, but on the handful of the largest and most massive subhalos predicted to orbit within the Milky Way's dark matter sphere. According to our most advanced simulations, these particular halos are true giants. They possess such immense gravitational wells, such deep pits of dark matter, that they should have easily overcome the early universe's hostile radiation. They are, in essence, too big to fail at the task of galaxy formation. The simulations suggest that these colossal subhalos should have readily pulled in vast amounts of gas, birthing bright, star-filled dwarf galaxies that would be among the most luminous satellites we see today. Yet, when we survey the actual dwarf galaxies around our Milky Way, like the Draco or Ursa Minor dwarfs, they are remarkably faint and contain far fewer stars than these simulated monster halos should host. The discrepancy is in the dynamics. By measuring the velocities of stars within these observed dwarfs, we can weigh them, calculating the total mass, mostly dark matter, that must be present to hold them together. The real dwarfs we see have significantly lower masses than the simulated too-big-to-fail halos. It's as if our cosmic blueprint predicted the existence of several gravitational titans, each capable of building a bustling island city, but when we look, we only find a few modest towns. These predicted giants appear to be missing, or at the very least, they are wearing a surprisingly convincing disguise. This isn't just a problem of counting, it's a problem of scale, suggesting a fundamental flaw in either our understanding of dark matter's inherent properties or in the complex physics of how galaxies are born. One avenue to resolve this tension is to reconsider the very nature of dark matter. What if it isn't entirely cold and collisionless? If dark matter particles had a small ability to interact with each other through some unknown dark force, this self-interaction could have profound effects. These particle collisions would generate a form of pressure, transferring heat from the dense inner regions of a halo to its outer edges. This process would effectively puff up the halo, making it larger and less dense in its core. A simulated halo that starts as a dense, compact heavyweight could, over billions of years of internal interactions, evolve into a more spread out, lighter-seeming structure, one that aligns much better with the masses we infer from the faint dwarf galaxies we actually observe. This idea elegantly solves the problem by allowing the massive halos to exist, but in a form that doesn't contradict the stellar motions we measure. However, another compelling solution lies not in changing dark matter, but in refining our models of cosmic history. The too-big-to-fail problem is primarily an issue of timing and environment. Our simulations often model the Milky Way's dark matter halo in isolation, but the real galactic neighborhood has a violent past. The most massive subhalos, due to their size, would have been the first to form and fall into the growing gravitational grasp of the young Milky Way. As they plunged inward, they would have experienced intense tidal forces, the same kind of gravitational stretching that the Moon causes on Earth's oceans, but on a cosmic scale. The Milky Way's immense gravity would have systematically stripped away the outer layers of dark matter from these infalling halos, reducing their total mass and density. Furthermore, the same supernova feedback that may solve the core cusp problem could have been particularly effective at ejecting gas from these relatively small systems, preventing them from forming the abundant stars we might otherwise expect. In this scenario, the massive halos are not missing. They have been sculpted and diminished by billions of years of interaction with their galactic host. Intriguingly, a potential observational breakthrough has come from the discovery of a completely new class of objects, ultra-diffuse galaxies. These are ghostly galaxies, some as large as the Milky Way but containing only 1% of its stars. They are incredibly faint, their light smeared across vast areas of space. For a long time, they were invisible to our telescopes, but with advanced instruments like the Dragonfly telephoto array, which is specifically designed to detect extremely low surface brightness objects, we are now finding them in large numbers, particularly in dense galaxy clusters. The revelation is that some of these ultra-diffuse galaxies appear to be incredibly massive, harboring enormous amounts of dark matter despite their lack of stars. They may, in fact, be the very too-big-to-fail halos we've been searching for. These are not failed galaxies. They are galaxies that succeeded in building a massive dark matter halo, but for reasons we don't yet fully understand, failed to convert most of their gas into stars. They represent a pathway of galactic evolution we never knew existed, showing that a massive halo does not necessarily guarantee a bright galaxy. The too-big-to-fail problem is therefore transforming from a crisis for our models into a guiding light, pointing us toward a more nuanced understanding of the intricate and often subtle relationship between the dark universe and the lighted one we call home. If the dark matter web is the universe's true skeleton, then its precise anatomy, the way this invisible mass is distributed from the grandest filaments to the densest nodes, is our next great puzzle. How does something that interacts only through gravity arrange itself into such a complex and specific architecture? The story of this distribution begins not with galaxies or clusters, but in the first fleeting moments after the Big Bang in a sea of near-perfect uniformity. At that time, the cosmos was an incredibly hot, dense, and smooth soup of particles and energy, but it wasn't perfectly smooth, thanks to quantum fluctuations, tiny, random variations in energy that occurred when the universe was smaller than an atom. There were minuscule differences in density from one point to another. These imperfections were the seeds of all future structure, ripples in the fabric of the newborn cosmos. Gravity is the great amplifier of these ripples. Over hundreds of millions of years, it began to act on these slight overdensities. Regions that had just a little bit more mass exerted a slightly stronger gravitational pull, drawing in surrounding dark matter and gas. As these regions grew denser, their gravitational pull intensified, accelerating the process in a powerful feedback loop. This gravitational collapse is what sculpted the cosmic web. The dark matter flowed along the gravitational contours of the early universe, settling into a vast network. Think of it like water finding its way across a complex landscape. It collects in the deepest valleys, forming rivers and lakes while leaving the highlands dry. In the cosmic context, the dark matter collected along specific pathways, forming the filaments, and pooled at the intersections of those filaments, creating the massive nodes where we find giant galaxy clusters today. The ordinary matter, the gas that would eventually form stars, simply followed the dark matter into these gravitational wells, lighting up the underlying structure. This process results in a very specific pattern of distribution. The vast majority of dark matter exists in the diffuse filaments that stretch across the cosmic void. These are the cosmic highways, immense but relatively low-density rivers of invisible mass. The greatest concentrations, however, are found in the nodes, the hubs where multiple filaments converge. It is here that dark matter reaches its peak density, creating the deep gravitational pits that can trap thousands of galaxies into a single cluster. This pattern is not random. It is a direct consequence of the initial conditions of the universe and the relentless, patient work of gravity. By studying the statistical distribution of galaxies, mapping where they cluster and where they are absent, we can essentially perform a cosmic autopsy, reverse engineering the properties of the dark matter that dictated their placement. Yet, when we compare our exquisitely detailed maps of the real universe to the predictions of supercomputer simulations, we find a fascinating and unexpected detail that challenges our assumptions. While the large-scale web matches beautifully, a closer look at the inner workings of individual galaxy clusters reveals a surprising smoothness. According to many simulations, the dark matter within a massive cluster should exhibit a certain amount of substructure or clumpiness. As smaller groups of galaxies fall into the cluster, they should bring their own dark matter halos with them, which would survive for a long time, creating a lumpy, heterogeneous distribution within the larger cluster halo. It would be like stirring chunky peanut butter into a batter. You'd expect to still find some pieces. However, observations using gravitational lensing, the bending of light around these massive clusters, sometimes suggest that the dark matter distribution is smoother and more evenly mixed than the simulations predict. The batter appears more homogeneous. This discrepancy points to physics we may not be fully accounting for. One compelling explanation brings us back to the possibility of self-interacting dark matter. If dark matter particles can, in fact, collide with one another, these interactions would act as a mixing mechanism. As the cluster forms through the violent merger of smaller groups, the dark matter particles would scatter off each other, transferring energy and smoothing out any initial clumpiness. The result would be a more relaxed, uniform distribution, much like how shaking a container of mixed nuts will eventually settle them into a more even layer. This observed smoothness in some clusters is therefore a potential clue, a subtle fingerprint that could reveal a fundamental property of dark matter particles that gravity alone cannot explain. The precise texture of the cosmic web, from the grainy to the smooth, may hold the key to unlocking the hidden physics of the dark sector. Now we arrive at a mystery that extends far beyond the architecture of galaxies and into the very expansion of the universe itself, a puzzle so significant it has been called a crisis in cosmology, the Hubble tension. At its heart, this is a debate about a single number, the Hubble constant, which measures the current rate at which the universe is expanding. For decades, astronomers have worked to pin down this value with ever-increasing precision, but instead of converging on a single answer, our two most powerful methods have stubbornly refused to agree. It's as if two of the most accurate clocks in the world are ticking at undeniably different speeds, and we are left to wonder which one, if either, is telling the correct time. The first method builds a bridge to the early universe by studying the subtle patterns imprinted in the cosmic microwave background. The faint afterglow of the Big Bang scientists can work out the ingredients and properties of the infant cosmos. Using our extremely well-tested model of cosmic evolution, known as lambda cold dark matter, they can fast-forward this early universe simulation 13.8 billion years to predict what the expansion rate should be today. This method provides a very precise answer. The other approach is more direct, measuring the expansion rate in our local, contemporary universe. Astronomers use a cosmic distance ladder, a series of techniques that build upon one another to gauge the distances to nearby galaxies. They observe pulsating stars called Cepheids variables and cataclysmic stellar explosions known as Type Ia supernova, which have a known intrinsic brightness. By comparing how bright these objects appear to how bright they actually are, we can calculate their distance, and by measuring their redshift, how fast they are moving away from us. This local measurement consistently gives a higher value for the Hubble constant than the prediction from the early universe. The difference might seem small, only a few percent, but given the incredible precision of both methods, it is a glaring discrepancy that suggests something fundamental is missing from our model. This is where dark matter enters the stage. The lambda cold dark matter model is the foundation of modern cosmology, and it has been spectacularly successful at explaining the large-scale structure of the universe, including the cosmic web we've been exploring. But the Hubble tension implies that this model, as it stands, might be incomplete. If the early universe and the modern universe are giving us different answers, perhaps we need to tweak the physics of the early cosmos in a way that involves dark matter. One compelling idea is that dark matter might not have been entirely passive in the universe's first moments. What if certain types of dark matter could interact with other components of the primordial soup? Consider the possibility of interacting dark matter. In the standard model, dark matter is assumed to be almost entirely inert, interacting with normal matter only through gravity. But if some dark matter particles could interact with dark energy, the mysterious force driving the accelerated expansion, or even with a hypothetical dark radiation, this could have altered the expansion history of the universe in a subtle but crucial way. An early, fleeting period of such interactions could have changed the sound horizon, which is a fundamental ruler used to calibrate the early universe measurements from the cosmic microwave background. A small adjustment to this cosmic ruler would, in turn, change the predicted value for the Hubble constant today, potentially bringing it into alignment with the value we measure locally. It's a bit like recalibrating the starting point of our cosmic clock to make its ticking match what we observe now. Another fascinating avenue involves the nature of dark matter itself. Could the Hubble tension be a hint that dark matter is more complex than a single, simple particle? Some theoretical models propose that a small fraction of dark matter might be dark. This dark radiation would have behaved like light in the early universe, traveling at near light speed and influencing how quickly small density fluctuations could grow. The presence of this additional relativistic component would have left a distinct imprint on the cosmic microwave background and again shifted the predicted expansion rate. Exploring these possibilities forces us to consider that the dark sector, the collective term for dark matter and dark energy, might be a rich and complex world of its own, with its own particles and forces that we are only beginning to glimpse. The Hubble tension, therefore, is far more than a technical disagreement about a number. It is a powerful probe, a cosmic anomaly that may be our best clue yet to uncovering new physics that operates in the shadows, physics that could fundamentally reshape our understanding of the universe's entire history. But to truly appreciate the role of dark matter, we must travel back to a time before the first stars flickered into existence, to an era known as the Cosmic Dark Ages. The universe was a profoundly different place than, a vast, black, and relatively simple expanse. After the brilliant flash of the Big Bang had faded and the primordial plasma had cooled enough for atoms to form, the cosmos was filled with a uniform, dark fog of neutral hydrogen and helium gas. There were no light sources, no galaxies, no structures of any kind. Yet the seeds for everything were already there, sown by the quantum fluctuations we discussed earlier. In this perfect darkness, dark matter was the only active player with enough mass to begin pulling the universe together. Its gravitational pull was the engine of creation, the force that patiently gathered the diffused gas, concentrating it into the first potential cradles for stars. This process hinged critically on the temperature of the dark matter. As we mentioned, the fact that we see such a finely detailed cosmic web tells us the dominant form of dark matter must be cold, meaning its particles were moving slowly enough to be easily captured by even the smallest gravitational ripples. This slowness was everything. Cold dark matter could begin clumping together on very small scales almost immediately. These tiny dark matter halos acted as gravitational anchors, miniature pits that started to draw in the surrounding hydrogen gas. As these halos merged and grew, their gravitational wells deepened, pulling in more and more gas. The gas, however, behaved differently from the dark matter. It felt pressure and could heat up, creating a force that resisted collapse. For a galaxy to form, the dark matter halo had to achieve a critical mass, a gravitational pull strong enough to overcome the gas's internal pressure and drag it inward. The timing of the very first galaxies was therefore a direct consequence of the dark matter's properties. A universe with warmer, faster-moving dark matter would have seen this process delayed, potentially altering the entire subsequent history of cosmic evolution. Once a dark matter halo grew massive enough, the trapped gas at its center could finally collapse. This collapse was not gentle. It was a violent, rapid infall that generated immense heat and pressure, triggering the nuclear fusion that ignites a star. The first stars, known as population 3 stars, were likely behemoths hundreds of times more massive than our Sun, burning ferociously bright and dying young in spectacular supernova. This was a pivotal moment, not just for lighting up the universe, but for a process called reionization. The intense ultraviolet radiation from these first stars and galaxies began to blast apart the neutral hydrogen atoms that filled the cosmos, stripping away their electrons and turning the universe from an opaque fog back into the transparent void we see today. The efficiency and timing of this reionization epoch were directly governed by how quickly dark matter could assemble those first galactic building blocks. If dark matter had different properties that slowed down galaxy formation, reionization might have occurred later, which would leave a measurable imprint on the cosmic microwave background. The fact that our observations of this background align with the cold dark matter model is a powerful validation of its role as the prime architect of the cosmic dawn. However, just when we think we have a handle on this narrative, the universe presents us with a bizarre and seemingly contradictory phenomenon: galaxies that appear to have very little or even no dark matter at all. This discovery sent shockwaves through the astronomy community, because if dark matter is the essential scaffolding for galaxy formation, how can a galaxy exist without it? The first of these oddities, a faint, diffuse galaxy named NGC 1052 DF2, was found to have stars moving so slowly that the gravitational pull required to hold the galaxy together was almost exactly accounted for by the visible stars alone. There was no need for a massive dark matter halo. This was startling. It would be like finding a magnificent, freestanding building constructed without any internal support beams or foundation, seemingly defying the laws of physics. The existence of these dark matter-deficient galaxies is not a refutation of the dark matter model. Rather, it is a clue to a more complex and dynamic story of galactic evolution. The leading explanation involves a cosmic game of gravitational theft. Most of these strange galaxies are found near massive, neighboring galaxies. The theory is that they did form within their own small dark matter halos, just like any other galaxy. But as they orbited their giant companion, they ventured too close. The immense tidal gravity of the larger galaxy could have effectively stripped away the dark matter halo, much like a passing star can strip the gas from a comet. Because dark matter is diffusely distributed in a large halo, it is more easily pulled away, while the more compact collection of stars at the galaxy's center can remain relatively intact. The result is a galaxy that has been robbed of its dark matter, leaving behind a ghostly collection of stars that tells a tale of a violent gravitational encounter. This process highlights that galaxies are not isolated islands. They are part of a dynamic ecosystem where interactions can dramatically alter their fundamental composition. The presence of these dark matter-poor galaxies, rather than undermining our theories, actually provides a unique test. It offers evidence for the very phenomenon of tidal stripping that our models predict, confirming that dark matter is indeed a distinct physical substance that can be separated from the stars it once helped to gather. This search for dark matter takes us from the grand scale of the cosmos to the realm of the incredibly small, where particles themselves might hold the key. If dark matter is indeed a new type of particle, one of the most thrilling possibilities is that these particles could annihilate upon contact with one another. The concept is rooted in the principles of particle physics, where matter and antimatter counterparts, like an electron and its antiparticle, the positron, can collide and vanish in a flash of pure energy, converting their mass into other particles according to Einstein's famous equation. While dark matter might not have a distinct antimatter counterpart in the same way, it could be its own antiparticle. The principle holds. If two dark matter particles were to collide, they could annihilate each other, producing a shower of secondary particles that we can detect, such as gamma rays, neutrinos, or cosmic rays. This offers a brilliant strategy. Instead of trying to catch a single, shy dark matter particle, we can search for the fiery aftermath of their mutual destruction. Our own Milky Way galaxy is thought to be embedded within a vast spherical halo of dark matter, with the density of these particles increasing dramatically towards the galactic center. This makes the heart of our galaxy a prime hunting ground. Astronomers use powerful instruments tuned to see the high-energy universe to scan these dense regions for telltale signs of annihilation. The Fermi Gamma Ray Space Telescope, for instance, has been scanning the sky for over a decade, mapping the gamma ray light, the most energetic form of light in the universe. If dark matter particles are annihilating, they should produce a specific, smooth distribution of gamma rays emanating from the galactic center, with an energy signature that corresponds to the mass of the dark matter particle itself. It's like listening for a specific chord in a cosmic symphony, a chord that no known instrument should be playing. One of the most persistent and controversial signals in this search is known as the galactic center GVXS. Fermi data has revealed an unexpected glow of gamma rays at energies of around a few giga-electronvolts coming from the region around the Milky Way's core. This excess of radiation is smoother and more spread out than what would be expected from known point sources like pulsars. For a time, this signal looked like a perfect match for what annihilation from a dark matter particle with a mass about 30 to 60 times that of a proton would produce. The excitement was palpable as it seemed we might have our first indirect detection. However, the universe is rarely so straightforward. A more conventional explanation has gained traction. A previously unseen population of thousands of faint, spinning neutron stars called millisecond pulsars. These distant, dim objects could collectively produce a diffuse glow that mimics the expected dark matter signal. Distinguishing between a smooth dark matter halo and a collection of countless unresolved points is one of the greatest analytical challenges in modern astrophysics. The search extends beyond gamma rays to the most ghostly of particles, neutrinos. Deep in the ice of the South Pole, the Ice Cube Neutrino Observatory consists of thousands of sensors buried over a mile deep, waiting for the rare flash of light produced when a neutrino interacts with an atom in the ice. Neutrinos are ideal cosmic messengers because they travel in straight lines, unaffected by magnetic fields, pointing directly back to their source. If dark matter particles were to accumulate in the core of the Sun, trapped by its gravity, their annihilations there would produce high-energy neutrinos that could stream out and be detected by Ice Cube. The same could happen in the Earth's core or in the center of our galaxy. While no definitive signal has been found, the absence of these neutrinos has already helped scientists rule out certain masses and interaction rates for dark matter particles, steadily narrowing the search. These indirect searches represent a beautiful convergence of the largest and smallest scales of physics. We are using giant telescopes orbiting Earth and enormous detectors buried in polar ice to probe the fundamental nature of a substance that makes up most of the matter in the universe. The ambiguous signals, like the galactic center excess, are not failures but rather the cutting edge of discovery. They force us to better understand the complex astrophysical backgrounds of our own galaxy, to improve our models and to build even more sensitive next-generation instruments. Each potential signal is a mystery unto itself, a cosmic puzzle box that must be carefully pried open to see if it contains the secrets of the dark universe or a new understanding of the luminous one we thought we knew. While we scan the skies for the high-energy signatures of dark matter annihilations, a parallel and equally daring quest is unfolding right here on Earth, deep beneath our feet. This is the hunt for direct detection, an effort to catch a dark matter particle in the act of interacting with an atom of normal matter. Imagine trying to hear the faintest possible tap on a single window pane during a hurricane. That is the scale of the challenge these experiments face. The premise is deceptively simple. Our planet, as it orbits the Sun, is constantly moving through the Milky Way's vast halo of dark matter. From our perspective, it should feel like we are sailing through an invisible wind of these elusive particles. Every second, billions of them are predicted to be streaming through your body, through the ground, and through the entire Earth. Almost all of them will pass through completely unnoticed, but every once in a great while, according to the hope, one might just bump into the nucleus of an atom. To have any chance of hearing that infinitesimal bump, scientists must create the quietest places on Earth. This is why the most ambitious direct detection experiments are housed deep underground, in abandoned mines beneath mountains or inside massive tunnels. Locations like the Sanford Underground Research Facility in South Dakota or Italy's Gran Sasso Mountain provide a natural shield, with thousands of feet of solid rock overhead to absorb the constant rain of cosmic rays from space that would otherwise create an overwhelming background noise, completely drowning out the delicate signal they are trying to hear. Inside these subterranean caverns, researchers have built technological marvels of purity and sensitivity. The leading experiments with names like Xeno NNT, Lux Zeppelin, and Panda X all operate on a similar brilliant principle. At their heart is a massive vat, sometimes containing several tons of an ultra-pure liquid element like xenon, kept at frigid temperatures. The concept is to create a vast, pristine target and wait. If a dark matter particle, such as a WIMP, does indeed pass through the tank and collides with a xenon nucleus, the interaction will deposit a tiny amount of energy. This will cause two distinct signals, a quick flash of scintillation light as the atom is jostled, and a moment later, a small electrical charge as electrons are knocked loose. Sophisticated sensors lining the tank capable of detecting single photons will capture both the immediate flash and the delayed charge. By precisely timing these two signals and pinpointing their location in three-dimensional space within the tank, scientists can distinguish a potential dark matter collision from residual background radiation, such as trace amounts of natural radioactivity from the environment or the apparatus itself. Every aspect of these detectors is engineered to eliminate false alarms, making them the most sensitive dark matter microphones ever constructed. Yet, despite decades of effort and detectors that have grown exponentially more sensitive, the story of direct detection has been one of profound silence. The experiments have not found a definitive, repeatable signal. Each new, more powerful generation of detector has pushed the limits of what we know, not by discovering dark matter, but by ruling out vast swaths of possibilities. The results are presented as exclusion plots, elegant graphs that show, for a given mass of a hypothetical dark matter particle and a given probability of it interacting, that such a particle cannot exist because we would have seen it by now. These plots have steadily shrunk the allowed parameter space for WIMP, closing door after door that once seemed promising. This persistent null result is in its own way a major scientific discovery. It tells us that if dark matter is a WIMP, it is even more elusive, more weakly interacting than our most conservative models predicted. This puzzling lack of a signal forces us to confront several possibilities, each with profound implications. The first is that we might simply need to be even more patient. The interactions could be so exceedingly rare that even with tons of target material, we may need to wait for years or even decades to accumulate enough events to claim a discovery. The next generation of detectors, proposed to hold tens or even hundreds of tons of liquid xenon, are already in the planning stages to address this possibility. The second, more dramatic possibility is that we are looking for the wrong thing. The WIMP paradigm, while elegant, might not be the correct one. The focus may need to shift to lighter, more exotic candidates like axions, which would require completely different detection strategies, such as using powerful magnetic fields to convert them into detectable photons. A third and more unsettling idea is that dark matter's interactions with normal matter are even more idiosyncratic than we thought. Perhaps the particles only interact under very specific conditions that our current experiments aren't designed to probe. Some theories suggest dark matter might have a small electric charge or interact only with electrons rather than atomic nuclei. Others propose that the strength of the interaction could vary throughout the year as Earth's velocity changes relative to the galactic dark matter wind. This would create an annual modulation in the signal rate, a subtle seasonal effect that a few experiments have reported hints of, though these remain controversial and unconfirmed by the larger community. The ongoing silence from the major detectors is not a dead end. It is a powerful guide pushing the frontier of particle physics into new and unexpected territories and reminding us that the dark universe may be stranger than we ever imagined. To understand how dark matter orchestrated the grand theater of cosmic evolution, we need to wind the clock back to a pivotal moment, the era of recombination, about 380,000 years after the Big Bang. This was the moment the universe cooled enough for electrons to combine with protons, forming the first neutral atoms. In an instant, the cosmos, which had been an opaque, glowing fog of plasma, became transparent. The light released in that moment is the cosmic microwave background we detect today, a baby picture of the universe. But crucially, this newly transparent space was not entirely empty or uniform. Imprinted upon it were the faint gravitational blueprints of everything to come, tiny density variations that had been amplified by sound waves traveling through the primordial plasma. These ripples were the seeds, and dark matter was the water that would make them grow. While the ordinary matter, now neutral and able to travel freely as gas, was ready to start its journey, dark matter had a head start. For those first few 100,000 years, the intense pressure from radiation had prevented the normal matter from collapsing under its own gravity. But dark matter, being immune to this electromagnetic pressure, was already beginning to clump. It was silently gathering in the slightest over dense regions, laying the foundation for the cosmic web. This is the process of gravitational instability in action. A region with just a little bit more mass exerts a slightly stronger gravitational pull, drawing in more dark matter from its surroundings. As it gains mass, its pull strengthens, accelerating the process in a powerful feedback loop that turns a tiny ripple into a gravitational well. The first structures to form were minuscule dark matter halos, tiny gravitational pits that began to dot the young universe. Think of them as the earliest villages in a vast, empty landscape. Over hundreds of millions of years, these villages started to merge. Gravity pulled them together, forming larger and larger towns, then cities. This process, known as hierarchical structure formation, is the backbone of how the cosmic web was built from the bottom up. The dark matter acted as the framework, the underlying geography that dictated where the ordinary matter would eventually flow. The gas, made of hydrogen and helium, simply followed the gravitational contours carved out by the dark matter, falling into these growing halos. Once a halo reached a critical mass, the gas at its center could collapse, heat up, and eventually ignite the first stars, lighting up the dark matter scaffolding for the first time. The timeline of this evolution is a story written in the light of galaxies. The very first stars probably flickered on when the universe was only a few 100 million years old, ending the cosmic dark ages. Then, over the next several billion years, the universe entered its most active period of construction. The filamentary structure of the cosmic web became clearly defined as dark matter flowed along the gravitational landscape, creating vast rivers and highways connecting immense nodes where galaxy clusters would form. By the time the universe was about half its current age, the large-scale structure we see today was largely in place. The frantic pace of galaxy formation slowed, and the cosmos settled into a more stately evolution, with galaxies continuing to merge and evolve within the now mature dark matter architecture. This entire history is not just a narrative, it's a powerful laboratory for testing the fundamental nature of dark matter itself. The specific way the cosmic web evolved places incredibly tight constraints on what dark matter can be. For instance, the fact that small galaxies formed so early in the universe's history is strong evidence that dark matter is cold. If it were warm, composed of faster-moving particles, those early, small-scale clumps would have been smoothed out, delaying the formation of the first galaxies and producing a much different web pattern, one with fewer fine filaments. The precise statistics of the web, the sizes of the voids, the thickness of the filaments, the distribution of galaxy clusters act as a fingerprint. By comparing incredibly detailed maps of the real universe, like those from the Sloan Digital Sky Survey, to computer simulations that use different assumptions about dark matter, we can rule out entire classes of particles. A universe with strongly self-interacting dark matter, for example, would have a web with noticeably fatter filaments and less substructure than what we observe. Furthermore, the evolution of the cosmic web provides a critical testing ground for the most prominent alternative to dark matter, modified gravity theories. Proposals like modified Newtonian dynamics, or MOND, suggest that our understanding of gravity is incomplete, and that what we attribute to dark matter is actually a modification of gravity's behavior on very large scales. While MOND can successfully explain the rotation curves of individual galaxies, it struggles profoundly to account for the full complexity of the cosmic web. The intricate pattern of clusters and filaments, and particularly the observed separation between normal matter and the gravitational source in events like the bullet cluster, present a monumental challenge for these theories. The growth of structure in a MOND-like universe does not match the rapid, detailed formation we see etched across the sky. The cosmic web, therefore, stands as one of the most compelling pieces of evidence that we are not just missing a modification to gravity, but an entire, invisible component of the universe whose gravitational hand has been guiding cosmic evolution since the very beginning. While the evidence for a vast, invisible component of the universe is overwhelming, the fact that we cannot directly touch or see it has led a small but persistent group of scientists to ask a radical question: what if we've been thinking about this all wrong? What if the mystery of galactic rotation and the cosmic web isn't due to missing matter, but to a fundamental flaw in our understanding of gravity itself? This brings us to our 12th mystery, the compelling yet deeply challenged world of alternative theories to dark matter. The most prominent of these is modified Newtonian dynamics, or MOND. Proposed by physicist Mordechai Milgrom in the early 1980s, MOND offers a beautifully simple premise. Instead of inventing a new, invisible substance to explain why stars on the outskirts of galaxies orbit too fast, perhaps Newton's law of gravity, which has been spectacularly successful in our solar system, simply breaks down where gravity becomes incredibly weak. Milgrom suggested that on the scale of galaxies where the gravitational pull is minuscule, gravity switches to a different mode. It becomes stronger than Newton or Einstein would predict. This modification is designed to kick in at very low accelerations, precisely the conditions experienced by stars far from a galaxy's bright center. The remarkable thing is that with a single, tunable constant, MOND can beautifully predict the rotation curves of a wide variety of spiral galaxies. It's an elegant solution that works for the very problem that first pointed us toward dark matter. For its supporters, this is a sign of Occam's razor, the idea that the simplest explanation is often the best. Why fill the universe with a mysterious, undetected particle when a tweak to a well-known law could do the job? However, the cosmic evidence extends far beyond the rotation of individual galaxies, and this is where MOND and its cousins face their greatest challenges. The first major hurdle is the behavior of galaxy clusters. Remember, it was the immense gravity of these clusters, revealed by gravitational lensing and the motion of galaxies within them, that provided some of the earliest and strongest evidence for dark matter. When you apply MOND to a massive cluster, it still falls short. The modified gravity calculation does provide some extra pull, but not nearly enough to account for the observed gravitational strength. Proponents of MOND have had to propose that clusters contain some additional, unseen matter, not dark matter, but perhaps hot, diffuse gas or sterile neutrinos. This immediately complicates the elegant simplicity of the theory, requiring a missing matter problem of its own. An even more significant test comes from the cosmic microwave background, the afterglow of the Big Bang. The precise pattern of hot and cold spots in this radiation is a fingerprint of the universe's composition and geometry. Our standard model of cosmology, lambda cold dark matter, can reproduce this pattern with stunning accuracy. The model tells us that the oscillations in the early plasma were driven by the gravitational tug of war between the pressure of radiation and the gravity of both normal matter and dark matter. If you remove dark matter from the equation, as MOND does, the predicted pattern of the cosmic microwave background looks nothing like what we observe. To address this, any modified gravity theory must be integrated into a full relativistic framework, a task that has proven enormously difficult. While there are relativistic extensions of MOND, like TVS, they often introduce new fields and complexities, and even then, they struggle to match the precise cosmological data as cleanly as the standard model. Perhaps the most visually striking evidence against a pure modified gravity explanation is found in cosmic collisions like the famous Bullet Cluster. This system consists of two galaxy clusters that have smashed right through each other. When we observe it, we see something extraordinary. The most massive components of the clusters, the stars of the individual galaxies, passed by each other largely unaffected, like swarms of bees. The hot, X-ray emitting gas from each cluster, however, collided and got stuck in the middle, like two clouds of smoke merging. But when astronomers map the total mass using gravitational lensing, they find that the bulk of the mass is not with the gas in the center. It's with the galaxies that have already moved on. This is a direct observation of the separation between normal matter and the source of gravity. In the dark matter model, this makes perfect sense. The collisionless dark matter halos passed through each other, while the gas, which interacts electromagnetically, collided and lagged behind. For a modified gravity theory, this is a profound puzzle. If gravity is attached to the matter we see, the gravitational lensing effect should be strongest where the most matter is, which is the gas in the center. The fact that it isn't suggests that the gravity is following something invisible that has become separated from the visible material. So, where does this leave us? It seems both paths, invisible matter and modified gravity, face their own set of difficulties. Dark matter requires a particle that has eluded every direct detection experiment, while modified gravity struggles to explain the full breadth of cosmological evidence. This has led some theorists to wonder if the truth might lie in a hybrid approach. Could it be that our laws of gravity do need some refinement on the largest scales, and that there is an additional, non-luminous component to the universe? Perhaps dark matter is not a single, simple WIMP, but a more complex sector with its own interactions, and gravity itself has subtleties we have yet to master. Such a model would be immensely complex, but the universe has never shied away from complexity. The ongoing tension between these competing ideas is not a sign of failure in science, but a sign of its health. It represents a fierce debate at the frontier of knowledge, where every new observation from powerful telescopes like the James Webb Space Telescope provides fresh data that can tip the scales. This mystery forces us to question our most fundamental assumptions, and in doing so, drives us toward a deeper, more complete theory of the cosmos, one that may ultimately reconcile the seen and the unseen. As we probe the invisible architecture of the cosmos, our journey leads us to one of the most extreme environments imaginable, the gravitational monsters known as black holes. The relationship between dark matter and these cosmic abysses is a complex and fascinating puzzle. At first glance, their interaction might seem simple. A black hole's immense gravity should act as a perfect trap for dark matter, pulling in any particles that venture too close. Indeed, theoretical models suggest that dark matter would naturally form an ultra-dense cloud or spike around a black hole. As dark matter particles orbit, they would occasionally collide, losing a tiny amount of energy and sinking closer to the event horizon in a slow, inexorable process called gravitational relaxation. Over billions of years, this could create a halo of dark matter around the black hole that is many orders of magnitude denser than the average in the galactic halo. This accumulation could have significant consequences for the black hole itself. The additional mass from the captured dark matter could subtly influence the black hole's evolution, potentially causing it to grow more massive over time than models based solely on the accretion of normal matter would predict. Furthermore, if dark matter particles can annihilate with one another, as many theories suggest, the region around a black hole would be a prime location for this process. The incredibly high density within a dark matter spike would make particle collisions extraordinarily frequent. The energy released from this annihilation could, in theory, produce a detectable glow of gamma rays or other high-energy radiation. For a solitary black hole drifting in the emptiness of interstellar space, with no surrounding gas to accrete and produce light, this dark matter-powered emission might be its only signature. Astronomers have searched for this telltale signal from suspected black holes, but the results have been inconclusive, as other astrophysical processes can mimic the expected signature. This line of thinking leads to an even more radical idea. Could some black holes be dark matter? This is the intriguing hypothesis of primordial black holes. The theory proposes that in the incredibly dense and turbulent conditions of the very early universe, mere fractions of a second after the Big Bang, random fluctuations in density could have been so extreme that pockets of space collapsed directly into black holes. These wouldn't be the stellar mass black holes formed from dying stars or the supermassive giants at galactic centers. They could have a vast range of sizes, from smaller than an atom to many times the mass of our Sun. If vast numbers of these primordial black holes were forged in the first moment of time, they could, in principle, account for all or part of the dark matter we infer today. They would be invisible, massive, and would interact with the visible universe only through their gravity, fitting the basic description perfectly. However, this compelling idea runs into serious observational constraints. The primary tool for hunting for these isolated dark objects is a phenomenon called gravitational microlensing. If a primordial black hole were to pass directly between Earth and a distant star, its gravity would act as a tiny lens, bending the star's light and causing it to temporarily brighten. By monitoring millions of stars in nearby galaxies like the Large Magellanic Cloud, surveys such as the optical gravitational lensing experiment have placed strict limits on how many such objects could exist. The results show that while primordial black holes could make up a fraction of the dark matter, they cannot be the sole solution. Black holes with masses similar to a large asteroid are largely ruled out, as their microlensing signatures would have been abundantly seen. Similarly, very low-mass primordial black holes would have evaporated away by now due to Hawking radiation. The window for them to constitute all dark matter is narrow, limited to specific mass ranges, making it unlikely they are the dominant component. The relationship between dark matter and black holes, therefore, remains one of profound influence rather than identity, a dance of gravity and shadow where each entity deepens the mystery of the other. To uncover the deepest secrets of the dark matter web, we must learn to read the universe's oldest surviving text, the cosmic microwave background. This faint, cold glow is the cooled remnant of the universe's fiery birth, a snapshot of a time when the cosmos was just 380,000 years old. At that moment, the expanding universe had cooled enough for electrons to combine with nuclei, forming the first neutral atoms. In an instant, the foggy plasma that had filled space cleared, allowing light to travel freely for the first time. That ancient light has been stretching and cooling ever since, and today it bathes the entire sky in a microwave whisper, a uniform blanket with a temperature of just 2.7 degrees above absolute zero. But this background is not perfectly smooth. Etched upon it are tiny, millionth of a degree variations, the fingerprints of the infant universe's first struggles with gravity. These imperfections are not just random noise, they are an encoded message detailing the precise ingredients of the cosmos, including the exact amount and fundamental nature of dark matter. The key to decoding this message lies in understanding the acoustic oscillations that rippled through the primordial plasma. Imagine the early universe as a cosmic fluid, a seething mix of protons, electrons, photons, and dark matter. In this dense medium, gravity acted as the contracting force, constantly trying to pull matter together into denser clumps. But it was met with a powerful opposing force, the intense pressure of light or radiation. Photons pushed back against the gravitational collapse, creating a continuous tug of war. This struggle set the entire universe ringing like a bell. Regions of slightly higher density would collapse under gravity, but the resulting pressure increase would push the material back out, only for gravity to pull it in again. These rhythmic compressions and rarefactions were sound waves traveling through the cosmos. The most crucial detail is that dark matter was a passive but dominant participant in this dance. Because dark matter does not interact with light, it was immune to the radiation pressure. It could begin collapsing under gravity immediately, providing stable gravitational pits that anchored the oscillations of the ordinary matter. The distance these sound waves could travel in the time before the universe became transparent, a scale known as the sound horizon, became a fundamental cosmic ruler. When the universe finally became transparent, these oscillations were frozen in place, imprinted on the cosmic microwave background as a characteristic pattern of hot and cold spots of specific sizes. The most common angular scale for these spots corresponds directly to that sound horizon. By measuring the statistical distribution of these spots with exquisite precision, missions like the Planck satellite have been able to weigh the cosmic ingredients with incredible accuracy. The pattern tells us that ordinary matter, the atoms that make up stars and planets, accounts for only about 5% of the universe's total content. Dark energy, the mysterious force driving cosmic acceleration, makes up about 68%, and the remaining 27%, that is the dark matter. The data leaves no room for doubt. The gravitational effects needed to produce the observed oscillations require exactly that amount of an invisible, cold substance that clumped together early on. The cosmic microwave background is thus the single most powerful piece of evidence for the existence of dark matter, providing a complete inventory of the cosmos that matches perfectly with what we see in the large-scale structure of galaxies today. However, as with any profound discovery, the Planck data also revealed subtle anomalies, curious features that don't quite fit the predictions of our standard model. These are not errors, but tantalizing hints that there might be more to the dark sector than we currently understand. One of the most discussed is the so-called cosmic dipole anomaly. Our solar system is moving relative to the rest frame of the cosmic microwave background, which should cause a predictable, large-scale temperature difference across the sky. One hemisphere should appear very slightly warmer, the other cooler. But some analyses suggest this dipole might be stronger than expected, or that it might be aligned with other, unexpected large-scale structures in the universe. This could be a statistical fluke, or it could indicate a flow of dark matter on immense scales, a vast current within the cosmic web that is tugging on the distribution of galaxies and the cosmic microwave background itself in a way we haven't fully accounted for. Another intriguing puzzle involves the observed statistical properties of the hot and cold spots. According to the standard model, the fluctuations should be statistically isotropic, meaning they should look the same in every direction. Yet, some analyses suggest a possible alignment or axis, nicknamed the axis of evil, where the largest scale patterns seem to show a preferred direction. Furthermore, there are hints that the universe might not be as uniform as we think on the very largest scales. Some regions appear to have slightly different densities or expansion rates. These anomalies are faint, sitting at the very edge of statistical significance, and they could easily vanish with more precise data. But if they persist, they could point toward a more complex early universe, perhaps one with different types of dark matter that interacted in unique ways, or even a pre-Big Bang physics that left an imprint on our cosmos. The cosmic microwave background, therefore, is not a closed book. It is a living document, and its lingering mysteries assure us that the final chapter on dark matter is far from written. As we move from the cosmic microwave background to the present-day universe, we encounter the ultimate expression of dark matter's power, the galaxy cluster. These are the largest gravitationally bound structures in existence, colossal cities of galaxies containing hundreds or even thousands of individual members, all swimming in a vast sea of superheated gas and, most importantly, dominated by an immense halo of dark matter. Studying these giants allows us to observe dark matter's behavior on a grand scale, and in one spectacular case, a violent collision between two clusters provided what many consider to the most direct and visual proof of dark matter's existence as a physical substance. This brings us to the story of the Bullet Cluster, a system that has become a landmark in modern cosmology. The Bullet Cluster is the aftermath of a high-speed cosmic crash. Two galaxy clusters have collided, and the different components have behaved in a way that powerfully illustrates the distinction between ordinary matter and dark matter. The galaxies themselves, which are mostly empty space, passed right through each other with little interaction, like two swarms of bees flying through one another. The hot gas within each cluster, however, is a different story. This gas, which is ordinary matter in a plasma state, is so dense that when the clusters collided, the gas clouds smashed into each other. The collision created tremendous friction and pressure, slowing the gas down and causing it to pile up in the center of the merged system. We can see this gas clearly because it glows intensely in X-rays, observed by telescopes like the Chandra X-ray Observatory. So, after the collision, the most visible, tangible part of the clusters, the hot gas, is located in the middle. But then, astronomers mapped the total mass of the system using the technique of gravitational lensing. By observing how the cluster's gravity warps the light from more distant galaxies behind it, they could create a map of where the mass actually is. The result was stunning. The map revealed that the majority of the mass was not with the gas in the center. Instead, the gravitational lenses showed two distinct peaks of mass, each coinciding with the locations of the galaxy swarms that had already moved on. This was a clear separation. The normal matter, the gas, was in one place, stuck from the collision, while the source of the majority of the gravity, the dark matter, was in another place, having passed through unscathed. Why? Because dark matter, by its very nature, does not interact with itself or with normal matter through any force except gravity. It is effectively collisionless. The dark matter halos of the two clusters experienced no friction, no pressure. They simply passed through each other, following the galaxies. The bullet cluster collision effectively performed a natural experiment for us, cleanly separating the components of the universe. It demonstrated that most of the mass is in a form that is invisible and non-collisional, providing a compelling evidence that is very difficult for alternative theories of gravity to explain. However, the universe is rarely so simple, and another cluster presents a fascinating and counterintuitive puzzle. While the bullet cluster shows a clean separation, the cluster known as Abell 520, or the train wreck cluster, reveals a more mysterious configuration. Abell 520 is also the product of a complex multi-body collision. When astronomers mapped its components, they found something bizarre. There was a region in the center of the cluster that was rich in hot gas, as expected from a collision. But this region was also strangely devoid of galaxies. The galaxies had been flung out to the edges. When the gravitational lensing map was created, it showed a massive concentration of dark matter right in the same central region as the gas, but with no bright galaxies to account for it. This created a dark core, a knot of gravity that appeared to be associated with the gas but not with the stars of the galaxies. This discovery was perplexing. If dark matter is collisionless and simply follows the gravity of the galaxies, as it seemed to in the bullet cluster, why is there a huge clump of dark matter in the center of Abell 520 that has become separated from the galaxies? Several theories have been proposed to solve this mystery. One possibility is that this particular collision was far more complex, involving multiple clusters slamming together in a way that could have dynamically stranded the dark matter in the center through a complex gravitational slingshot effect. Another, more provocative idea is that this could be a hint that dark matter might have a very small but non-zero ability to interact with itself. In this scenario, dark matter particles could experience a kind of friction when they collide with each other, causing them to slow down and accumulate in the center of the merger, similar to how the normal gas did. This self-interacting dark matter model is a potential explanation for both the bullet cluster, where the interaction would be minimal, and Abell 520, where a specific set of collision parameters might have made the effect noticeable. The contrasting stories of the bullet cluster and Abell 520 highlight the dynamic and sometimes messy reality of cosmic evolution. They show that while we have a robust framework for understanding dark matter, its precise properties are still being revealed through these natural laboratories. The bullet cluster stands as a classic clean demonstration of dark matter's collisionless nature, while Able 520 serves as a tantalizing outlier, a clue that the dark sector might possess a richer physics than we have so far assumed. By studying a wide variety of clusters and their merger histories, astronomers are essentially conducting experiments on the fundamental nature of dark matter, using the universe itself as their laboratory. Each collision tells a story, and by reading these stories, we piece together the rules that govern the invisible majority of our cosmos. For most of cosmic history, the story of the universe has been one of construction, a grand assembly project directed by the relentless pull of gravity. Dark matter, as we have seen, was the master architect patiently gathering matter into the magnificent cosmic web. But this narrative of growth and structure has a counterpoint, a force that works in opposition to gravity's consolidating power. This brings us to our 16th mystery, which introduces the other dominant player in the cosmic drama, dark energy. While dark matter builds, dark energy pushes apart. Understanding the delicate and evolving balance between these two invisible giants is key to comprehending not only the universe's past but its ultimate fate. The influence of dark energy is a relatively recent development in the 13.8 billion-year history of the cosmos. For billions of years after the Big Bang, the universe was dense enough that gravity held sway. The expansion from the initial explosion was gradually slowing down as the gravitational attraction of all the matter, both dark and visible, pulled back on the fabric of space. Dark matter's gravitational wells were efficiently pulling galaxies and clusters together, allowing the cosmic web to grow ever more intricate and defined. But around 5 billion years ago, something profound changed. Observations of distant supernova revealed that the expansion of the universe was not continuing to slow down. Instead, it was beginning to accelerate. The universe had shifted into a new gear, and the driver of this acceleration was given the name dark energy. So, what is dark energy? In many ways, it is an even more profound mystery than dark matter. The leading hypothesis is that it is a property of space itself. Empty space, according to quantum physics, is not truly empty. It seethes with virtual particles popping in and out of existence. This vacuum energy could exert a kind of negative pressure, causing space to expand at an ever-increasing rate. Another possibility is that it is a dynamic energy field, dubbed quintessence, that changes over time. Whatever its nature, its effect is clear. It acts as a form of anti-gravity on cosmic scales. Think of it as a new, repulsive force that becomes significant only when the universe becomes large and diffuse enough. As the cosmos expanded and thinned out, the gravitational pull between galaxies weakened, while the push from dark energy, which is tied to the volume of space, grew stronger. About 5 billion years ago, these two forces reached a tipping point, and dark energy became the dominant influence. This transition has had a dramatic impact on the growth of the cosmic web. While dark energy does not directly destroy existing structures like galaxies or clusters that are already bound by gravity, it has effectively put a ceiling on the future growth of the large-scale structure. It acts as a cosmic embargo on the formation of new superclusters. Before dark energy's dominance, a galaxy cluster at the edge of a filament could continue to pull in matter from neighboring voids, steadily gaining mass. Now, as the space between galaxy clusters expands at an accelerating rate, those connections are being stretched and severed. The rivers of dark matter that feed the great nodes are being pulled taut. Galaxies on the outskirts of clusters are finding themselves isolated, their gravitational connection to the main body becoming too weak to overcome the ever-increasing stretch of space. The cosmic web is not being torn apart, but its future growth has been stunted. The universe is becoming a lonelier place where island galaxy clusters will drift ever further apart into an ever-darkening expanse. This leads to a profound question about the ultimate fate of the cosmic web, and indeed the entire universe. If dark energy remains constant, as the vacuum energy hypothesis suggests, the acceleration will continue indefinitely. This leads to a scenario known as the heat death or big freeze. Billions of years from now, all galaxies outside our local supercluster will be accelerated beyond our cosmic horizon, their light forever too redshifted and faint to detect. The universe will appear as an endless black void containing only our gravitationally bound cluster of galaxies. Eventually, even star formation will cease as gas is locked away in dead stars and black holes. The cosmic web, once a vibrant network of shining cities connected by luminous highways, will fade into a fragmented collection of isolated relics. If, however, dark energy is not constant but instead grows stronger over time, a scenario called the Big Rip, the outcome is far more violent. In this model, the repulsive force would eventually overcome all binding forces, not just between clusters but within them. Galaxies, solar systems, planets, and even atoms themselves would be torn apart in a final, catastrophic instant. The existence of these two dark components, matter and energy, that together make up 95% of the universe yet remain completely mysterious, has led physicists to wonder if they might be two sides of the same coin. Could there be a connection that simplifies our cosmological model? This is a tantalizing possibility. Perhaps dark matter and dark energy are not independent entities but are linked through a unified dark fluid. In some theoretical models, this fluid can behave like matter clumping under gravity in regions of high density, but like energy causing repulsion in the vast, empty voids. This would be an elegant solution, reducing two profound mysteries into one. Alternatively, the nature of dark energy might be intimately tied to the properties of the vacuum, and dark matter could be a particle that interacts with this vacuum energy in a unique way. So far, no such connection has been found, and the standard model of cosmology keeps them as separate ingredients. But the search for a deeper link is a driving force in theoretical physics, as finding one would represent a monumental leap in our understanding, potentially revealing a single, elegant principle governing the unseen 95% of reality. The interplay between the cosmic architect and the cosmic saboteur remains one of the greatest stories ever told, a narrative whose final chapters are being written in the dark. But perhaps the most powerful tool for reading our galaxy's dark matter story comes not from the living stars but from the dead. The Gaia spacecraft is providing us with an unprecedented map of the Milky Way, charting the positions and motions of nearly 2 billion stars. Within this vast celestial census, we are finding the ghosts of galaxies past, stellar streams. These are long, ribbon-like structures of stars, the torn-apart remains of smaller dwarf galaxies that ventured too close to the Milky Way's immense gravitational grip. Over billions of years, our galaxy's tides have stretched these intruders into elegant arcs that wrap around the galactic halo. These streams are more than just cosmic debris, they are exquisite gravitational sensors. Because the stars in a stream were all born together and travel on similar orbits, their path is exquisitely sensitive to the gravitational field they move through. Any lumpiness or asymmetry in the dark matter halo will subtly distort the stream, causing gaps, kinks, or changes in its density. By meticulously measuring these distortions with Gaia, astronomers are essentially performing a tomography scan of the Milky Way's dark matter distribution. It's like dropping a series of floating markers into a river to map its underwater currents. The stellar streams trace the invisible flow of gravity. Early results are already challenging our models. Some streams appear remarkably smooth and coherent, suggesting the inner dark matter halo might be more evenly distributed than simulations predict. Others show tantalizing signs of perturbations that could be the fingerprints of those predicted but unseen dark subhalos, the invisible clumps of dark matter that should be orbiting within the larger halo. Each stream tells a story of a galactic encounter and, in its precise geometry, encodes a detailed record of the dark matter forces that have shaped it. As we chart more of these stellar fossils, we are writing the biography of our galaxy, a story where the primary character remains unseen, but whose influence is etched into the very motions of the stars we can see. Our journey into the dark has taken us from the vastness of the cosmic web to the heart of individual particles, but now we must venture into a realm where the rules of reality itself become strange and counterintuitive, the quantum world. So far, we've largely discussed dark matter as if it were composed of discrete particles like tiny, invisible billiard balls. But what if, on the scales that truly matter, this picture is fundamentally incomplete? Our 18th mystery asks whether quantum phenomena, which typically govern the behavior of the very small, might play an unexpected and decisive role in the behavior of the very large, shaping the universe on galactic scales. This possibility opens up a fascinating new frontier where the ghostly nature of quantum mechanics could be written across the cosmos. The most compelling idea in this quantum realm is that dark matter might not be particulate at all, but rather wave-like. This concept is central to a class of models known as fuzzy dark matter or wave dark matter. The proposal is that the dark matter particle could be extraordinarily light, billions of times lighter than an electron. When a particle is that light, its quantum mechanical wavelength, a measure of its fuzziness and spread in space, becomes incredibly large. Instead of behaving like a point-like bullet, such a particle would behave more like a diffuse wave spread out over a vast area. On the scale of a dwarf galaxy, this quantum wave could be light years across. In this model, what we call a dark matter halo is not a swarm of individual particles, but a single, gigantic quantum wave vibrating in a gravitational well. This isn't just a theoretical curiosity. It could directly solve some of the small-scale problems we've encountered, like the core cusp issue. The inherent fuzziness and wave-like nature of the matter would naturally prevent it from collapsing into an infinitely dense point, creating the soft central cores we observe instead of the sharp cusps predicted by simple particle simulations. Take this quantum idea a step further, and we arrive at an even more spectacular possibility: a Bose-Einstein condensate on a galactic scale. A Bose-Einstein condensate is a unique state of matter that occurs when a gas of certain particles, called bosons, is cooled to near absolute zero. Under these conditions, the individual quantum waves of the particles overlap and synchronize, causing them to lose their individuality and merge into a single, coherent quantum object that behaves as one giant wave. If the dark matter particle is a boson and ultralight, the conditions of deep space, which is itself incredibly cold, might be sufficient for the entire dark matter halo of a galaxy to enter this condensed state. Imagine the halo of the Milky Way not as a cloud of discrete particles, but as a single, ghostly superfluid, a quantum wave function of astronomical proportions. This superfluid would have unique properties like zero viscosity, which could explain the smoothness of dark matter distributions within galaxy clusters. Any clumpiness or substructure would be naturally smoothed out by the coherent behavior of the condensate. These quantum aspects would have profound implications for how we search for dark matter. The direct detection experiments we discussed, which look for the nuclear recoil from a particle collision, are designed for heavy, particle-like WIMP. They would be completely blind to an ultralight wave like dark matter. A wispy quantum wave washing over a xenon atom would be far too gentle to give it a noticeable kick. Instead, the hunt would shift dramatically. Scientists would need to look for much more subtle effects. If dark matter is such a field, it could interact with ordinary matter not through violent collisions, but by causing tiny oscillations in the fundamental constants of nature, like the mass of the electron or the strength of the electromagnetic force. Exquisitely sensitive laboratory experiments using atomic clocks or laser interferometers could, in principle, detect these incredibly slight rhythmic variations. Furthermore, the wave-like nature of fuzzy dark matter would leave a distinct imprint on the structure of the cosmic web. The quantum pressure associated with the wave would suppress the formation of structure on very small scales. This would mean a scarcity of very tiny dwarf galaxies, which is exactly what we see in the missing satellites problem. The large-scale web would remain, but the fine, granular details would be washed out like a photograph with a slightly soft focus. By comparing ultra-precise maps of the universe's structure to simulations of wave dark matter, astronomers are already placing constraints on how light such a particle could be. This quantum perspective challenges our classical intuition at every turn and forces us to consider that the dark sector might be governed by a physics far richer than we ever imagined. It suggests a universe where the line between the very small and the very large is blurred, where galactic halos are not just gravitational structures but also quantum mechanical objects. The search for dark matter is therefore not just a hunt for a missing particle. It is a fundamental inquiry into whether the quantum weirdness that defines the subatomic world also sculpts the grandest structures of the cosmos. To truly grasp the influence of dark matter, we must journey back to the universe's first few minutes, a period known as Big Bang nucleosynthesis. This was the brief, fiery window when the entire cosmos was hot and dense enough to act as a nuclear fusion reactor, forging the lightest elements, hydrogen, helium, and a trace amount of lithium. The outcome of this primordial cooking session was exquisitely sensitive to the conditions of the early universe, particularly how quickly it was expanding and how many particles were vying for space. This is where dark matter enters the picture, even at this incredibly early stage. If dark matter were too abundant or interacted too strongly with the primordial plasma, it would have altered the expansion rate and the density of particles, changing the predicted amounts of these light elements. The remarkable agreement between the observed cosmic abundances of helium and deuterium and the predictions of a model where dark matter is largely passive during this epoch places a powerful constraint on its properties. It tells us that whatever dark matter is, it could not have been significantly annihilating with itself or otherwise dumping large amounts of energy into the plasma during those first critical minutes. The recipe for the universe's first atoms worked perfectly with dark matter as a silent, background ingredient, confirming its role as a substance that primarily makes its presence known through gravity alone. After nucleosynthesis, the universe entered the long, dark ages, a period spanning hundreds of millions of years when no stars shone, but dark matter was far from idle. While the ordinary matter, now a neutral gas of hydrogen and helium, was held back by pressure, dark matter, unaffected by these forces, was already collapsing under its own gravity. The specific properties of dark matter govern the timing and nature of this collapse, which in turn dictated when the first stars would finally ignite. This is the critical link between the invisible universe and the cosmic dawn. If dark matter were cold, made of slow-moving particles, it would have begun clumping on very small scales almost immediately. These tiny gravitational wells acted as seeds, gathering more matter and merging to form the first protogalaxies. A universe dominated by cold dark matter predicts that the first stars should have flickered on when the universe was only a few 100 million years old. However, if a significant portion of dark matter were warm, consisting of faster-moving particles, it would have streamed freely across the early universe, washing out those small-scale clumps. This would have delayed the formation of the first gravitationally bound structures, pushing back the era of first light. The fact that we observe galaxies and quasars at extremely high redshifts, meaning they existed very early on, strongly favors a model where the dominant form of dark matter is cold, providing the necessary early gravitational anchor for cosmic structure. The ignition of those first stars was not just about lighting up the darkness. It triggered a cosmic revolution known as reionization. These first stars, likely monstrously large and ferociously bright, flooded the universe with intense ultraviolet radiation. This radiation began to tear apart the neutral hydrogen atoms that filled intergalactic space, stripping away their electrons and reionizing the gas, turning the universe from an opaque fog back into the transparent void we see today. The timing and duration of this reionization epoch, which we can measure by studying the absorption of light from the most distant quasars, is another crucial test for dark matter. If dark matter had properties that accelerated structure formation, reionization would have started earlier and proceeded more rapidly. If it suppressed small galaxies, reionization would have been delayed. Current observations suggest reionization was largely complete by the time the universe was around 1 billion years old, a timeline that fits well with the cold dark matter model and its prediction of an early and abundant population of small, star-forming galaxies. Now, with the James Webb Space Telescope, we have a time machine capable of directly observing this pivotal era. JWST's unprecedented infrared sensitivity allows it to peer back and see the very first galaxies in their infancy. By studying these primordial systems, we are conducting a direct test of our dark matter models. JWST is already revealing a surprising abundance of bright, massive galaxies at redshifts higher than we had anticipated. This has sparked a fascinating debate. Does this mean our understanding of how quickly galaxies can assemble is flawed, or could it point to something about the nature of dark matter itself? Some theorists suggest that these surprisingly bright early galaxies could be explained if dark matter has small-scale clustering properties that differ from the simplest models, perhaps due to interactions or wave-like effects that enhance star formation efficiency in the earliest halos. Every new deep field image from JWST is not just a pretty picture. It is a data point that helps us refine our understanding of how the invisible scaffolding of dark matter guided the construction of the first luminous structures in the cosmos, bringing the dark ages to a dramatic close. Looking ahead, the quest to unmask dark matter is accelerating, propelled by a new generation of instruments so powerful they promise to explore territories of physics and the cosmos we have only ever dreamed of. This 20th mystery, the future of the search itself, is not about a single experiment but a coordinated global campaign attacking the problem from every conceivable angle. The strategy is multi-pronged. We will push the sensitivities of underground detectors to unprecedented limits, scan the skies with telescopes of breathtaking scope, hunt for exotic particles in colossal colliders, and even listen for the whispers of dark matter in the echoes of cosmic collisions. This is a golden age of exploration, and the next decade could very well deliver the breakthrough we have been seeking for nearly a century. On the direct detection front, the experiments that have so far returned only profound silence are preparing for a monumental leap. The next phase, often called the ultimate generation of liquid xenon detectors, is already in advanced planning. Projects like Darwin and a potential upgrade to the LZ experiment aim to deploy tanks containing not just a few tons but 30, 50, or even 100 tons of ultra-pure xenon. By scaling up the target mass to such an immense size, scientists dramatically increase the probability of a rare interaction, essentially making the detector's ear vastly more sensitive. These behemoths will be so quiet and so precise that they will probe regions of parameter space where the interaction rate could be as low as 1 event per century in their entire mass. If a WIMP-like particle with the properties predicted by some supersymmetry models exists, these instruments should be capable of hearing its faint tap. If they still find nothing, it will be a result of monumental importance, effectively closing the book on a wide class of WIMP models and forcing a major pivot in the field toward even more exotic possibilities. Simultaneously, the search is expanding to target lighter and more elusive candidates. As the WIMP paradigm faces challenges, interest in ultralight particles like axions has surged. Here, the approach is completely different. Instead of waiting for a nuclear recoil, experiments like the Action Dark Matter experiment, or ADMX, use a powerful superconducting magnet to create a strong magnetic field. The theory is that an action passing through this field could convert into a faint microwave photon. It's like tuning a cosmic radio to an extremely specific, unknown station. ADMX and its successors are meticulously scanning through millions of possible frequencies, searching for that one telltale whisper that would signal the presence of an action wind blowing through the lab. Other innovative tabletop experiments are searching for even lighter particles by looking for minuscule oscillations they might induce in the fundamental constants of nature, using exquisitely stable lasers and atomic clocks as their detectors. The frontier of direct detection is no longer a single path. It is branching into a diverse ecosystem of technologies, each tailored to a different hypothetical fragment of the dark universe. In the realm of particle colliders, the hope is to create dark matter, not just detect it. The Large Hadron Collider, which famously discovered the Higgs boson, continues its quest by smashing protons together at nearly the speed of light. The strategy here is indirect. If dark matter particles are produced in these collisions, they would be invisible to the detectors, slipping away without a trace. However, their presence would be betrayed by a telltale imbalance in momentum, a significant amount of energy and momentum that seems to vanish from the event, carried away by the invisible particles. Physicists scour the collision data for these missing energy signatures. While no definitive signal has emerged, the LHC has already placed stringent constraints on the possible masses and interaction strengths of potential dark matter particles. Future upgrades to the LHC and proposals for even more powerful colliders, like a future circular collider with a circumference of 100 kilometers, will push the energy frontier further, potentially creating particles far beyond the reach of current technology and finally opening a window into the dark sector. But perhaps the most dramatic advances will come from our view of the sky. Astronomy is undergoing a revolution with the advent of new observatories that will map the cosmos with staggering detail. The Vera Rubin Observatory's Legacy Survey of Space and Time, or LSST, will photograph the entire southern sky every few nights for a decade, creating an unprecedented motion picture of the universe. This colossal dataset will allow us to track billions of galaxies and use weak gravitational lensing to create the most precise map ever of the dark matter distribution across the universe. It will find millions of new gravitational lenses, revealing the substructure of dark matter halos in exquisite detail and providing a powerful new test for theories like self-interacting dark matter. At the same time, the European Space Agency's Euclid Space Telescope is conducting a similar survey from orbit, free from the blurring effects of Earth's atmosphere, to measure the shapes of galaxies and the geometry of the cosmic web with exquisite precision. Together, these missions will measure the effects of dark matter and dark energy with such accuracy that they could reveal subtle inconsistencies with our standard model, pointing the way toward new physics. This new era is also the dawn of multi-messenger astronomy, where we combine different cosmic signals to gain a deeper understanding. The detection of gravitational waves, ripples in space-time from cataclysmic events like black hole mergers, has opened an entirely new sense with which to perceive the universe. Now, scientists are exploring how dark matter might influence these signals. For instance, if dark matter accumulates around black holes, it could subtly alter the gravitational wave signal as the black holes spiral together. Furthermore, if a neutron-star merger is observed simultaneously in gravitational waves and light, any delay between the two signals could be a clue. If the gravitational waves pass through a dense clump of dark matter on their way to Earth, they would be slightly slowed, creating a lag that could betray the presence of the invisible material. By correlating gravitational wave events with observations from gamma-ray telescopes, optical telescopes, and neutrino detectors, we can conduct entirely new kinds of experiments, using the cosmos itself as a laboratory to probe the nature of dark matter in ways that were unimaginable just a few years ago. The future of dark matter research is therefore a story of convergence. It is no longer a niche field for a few specialists. It is a central puzzle that brings together particle physicists, astrophysicists, and cosmologists. The path forward is paved with both immense technological ambition and the thrilling possibility of profound discovery. Whether the answer comes from a vat of liquid xenon a mile underground, a magnetic resonator tuned to a ghostly frequency, a torrent of data from a survey telescope, or the subtle echo of a gravitational wave, one thing is certain: the mystery of dark matter will not remain a mystery forever. The tools now being built are the ones that will finally illuminate the dark, revealing the true nature of the universe's hidden architecture and forever changing our place within it. But as we chart the influence of this invisible substance on the grandest scales, from the birth of galaxies to the fate of the cosmos, a deeply personal question arises: what does dark matter mean for us? This leads to our 21st mystery, a foray into the realm of profound speculation. Could dark matter have played a role in our own existence? Is it possible that this hidden architecture of the universe is not just a backdrop, but an active participant in the story of life itself? While the idea might sound like science fiction, scientists are seriously considering the ways in which dark matter's subtle touch might have been essential to making the universe a habitable place, or conversely, could pose a hidden threat. Let's begin with the cosmic prerequisites for life. For a planet to support biology as we know it, it needs a stable environment around a long-lived star, and it needs a rich supply of heavy elements: carbon, oxygen, iron, and more forged in the hearts of stars and scattered across space by supernova explosions. This is where dark matter's primary role becomes clear. Without the immense gravitational wells of dark matter, the ordinary gas in the early universe would have diffused too slowly to collapse into the first galaxies and stars. The universe would have remained a thin, dark soup, with star formation proceeding at a glacial pace. The rapid assembly of structure, driven by dark matter, ensured that generations of stars could live and die quickly, enriching the cosmos with the necessary ingredients for planets and life within a few billion years. In this fundamental sense, dark matter was the indispensable cosmic contractor that built the galactic cities where life could eventually arise. It created the gravitational nurseries where stars like our Sun could form, surrounded by a disk of material containing those vital heavy elements, allowing rocky planets like Earth to coalesce. But could dark matter's influence be more direct? One fascinating hypothesis involves the very stability of our solar system. The Sun orbits the center of the Milky Way, but its path is not a simple circle. It oscillates up and down through the galactic plane. Some theorists have suggested that the gravitational pull of the dark matter halo could have a stabilizing effect on these oscillations, potentially protecting the solar system from gravitational perturbations that might otherwise fling comets from the distant Oort cloud into the inner solar system, causing catastrophic impact events. In this view, the smooth distribution of dark matter might act as a gravitational cushion, providing a more stable long-term environment for life to evolve undisturbed. On the other hand, if the local dark matter distribution were clumpier, with dense subhalos passing through our region of the galaxy, the opposite could be true. Such gravitational encounters might disrupt the Oort cloud, triggering showers of comets that could increase the rate of mass extinctions. The history of life on Earth, with its periodic catastrophes, might bear the subtle imprint of our solar system's journey through the invisible topography of the dark matter web. Then there is the possibility of direct physical interaction. We are constantly bathed in a wind of dark matter particles. What if, on incredibly rare occasions, they do more than just pass through us unnoticed? Some models suggest that if dark matter particles are light enough and have a very small coupling to ordinary matter, they could deposit tiny amounts of energy inside living cells. The probability of such an interaction causing a meaningful effect is astronomically low, but over billions of years and across countless organisms, could it have acted as a source of genetic mutation? It is a fringe idea, but it proposes that dark matter could be a very faint background source of evolutionary pressure, a whisper of randomness from the dark sector that occasionally introduces a new variation into the genome. While this is highly speculative and vastly overshadowed by other sources of mutation like cosmic rays and chemical processes, it is a reminder of the countless ways the universe might interact with biology on levels we are only beginning to imagine. This line of thinking also leads to a more ominous possibility. What if there are places in the galaxy where dark matter is so concentrated that it becomes dangerous? We've discussed the dense spikes that could form around black holes. If dark matter particles can annihilate with each other, such a region would be flooded with intense radiation gamma rays, X-rays, and energetic particles. A planet orbiting a star that wandered into such a zone would be sterilized, its atmosphere stripped away and its surface bombarded by lethal energy. This could create dead zones within the galaxy, regions where the dark matter architecture itself makes the emergence of complex life impossible. The habitable zone for life may not only be about the distance from a star, but also about a solar system's location relative to the invisible geography of the dark matter web. Conversely, could this annihilation energy be harnessed? If a technologically advanced civilization were to somehow gather and concentrate dark matter, they might be able to initiate a controlled annihilation process, tapping into a power source far beyond anything nuclear fusion could offer. This would be energy derived not from the limited reservoir of visible matter, but from the vast ocean of dark matter that permeates the galaxy. Such a civilization would truly have learned to build with the universe's hidden foundations, using the dark architecture itself to power its endeavors. While this remains firmly in the domain of theoretical astrophysics and science fiction, it highlights a profound point. Understanding dark matter is not just an academic exercise. It is an exploration of the fundamental resources and conditions that have shaped our past and might one day define our future. The answer to the mystery of dark matter could ultimately tell us whether it is a silent partner in the story of life, a neutral bystander, or a hidden force that has actively guided the evolution of the cosmos toward consciousness. As we map the known territories of the dark matter mystery, we must also turn our attention to the cosmic anomalies, the strange and fleeting events that defy easy explanation. These are the astrophysical oddities that pepper our observations, phenomena so bizarre they compel scientists to ask a daring question. Could some of these be the faint, distorted signatures of dark matter itself? This line of inquiry forces us to walk a delicate line, carefully distinguishing between the truly unknown and the merely not yet understood, all while searching for a ghostly signal in a universe filled with natural fireworks. Consider the enigma of fast radio bursts. These are incredibly brief, immensely powerful blasts of radio waves that last only a few thousandths of a second. Yet in that instant, they can release as much energy as the sun does in 80 years. They arrive from deep space, from galaxies billions of light years away, and for the most part they appear to be one-off events. While astronomers have identified some sources, like highly magnetic neutron stars called magnetars, as the origin for some of these bursts, a significant fraction remain unexplained. Could a population of exotic dark matter objects be responsible? One speculative idea involves hypothetical entities like action stars. If dark matter is made of ultralight axions, they could theoretically condense into dense star-like clusters. If such a cluster were to encounter a strong magnetic field, say from a neutron star or a black hole, it could undergo a catastrophic collapse, converting a substantial portion of its mass into a burst of radio waves in a process that would perfectly mimic a fast radio burst. The challenge is that magnetars provide a perfectly viable, conventional explanation for many bursts, so to claim a dark matter origin, we would need to identify a subset of bursts with properties that are utterly impossible for any known astrophysical object to produce a burst from an empty region of space, or one with a unique energy signature that points to a particle decay. Then there are the ultra-high-energy cosmic rays, subatomic particles that streak through the universe with energies millions of times greater than anything we can produce in our most powerful particle accelerators. The origin of these cosmic cannonballs is a major puzzle. What natural engine in the universe can accelerate a single proton to such phenomenal speeds? Conventional candidates include the environments around supermassive black holes or the shockwaves from galaxy collisions. But what if the source is more exotic? The annihilation or decay of a super-heavy dark matter particle is a tantalizing possibility. If dark matter consists of particles with masses trillions of times heavier than a proton, a single decay event could, in principle, produce a shower of particles including these ultra-high-energy cosmic rays. The advantage of this hypothesis is that it could explain why we see these rays coming from seemingly empty space without a clear astrophysical source nearby. The dark matter halo of our own Milky Way would be filled with such particles, and their decay would be a continuous, isotropic background. However, the search is complicated by the fact that these ultra-high-energy particles are deflected by magnetic fields as they travel, making it incredibly difficult to trace them back to their precise point of origin. Pinpointing a source is key. If a significant number of these rays were traced back to the diffuse halo of our galaxy rather than to distant active galaxies, the case for a dark matter connection would grow much stronger. This highlights the fundamental challenge of this entire endeavor, the need for a perfect understanding of conventional astrophysics. Before we can claim a discovery of new physics, we must be certain we have exhausted all possible natural explanations. The history of science is littered with examples of dark matter signals that later turned out to be fascinating but ordinary astrophysical processes. A classic case is the long-standing puzzle of the gamma-ray glow from the center of our galaxy, which for a time looked like a promising signal for dark matter annihilation. As we discussed, further analysis strongly suggested it was more likely caused by a vast population of unresolved millisecond pulsars. This isn't a failure, it's the scientific process at work. Each time we rule out a dark matter explanation for an anomaly, we not only refine our search parameters but also deepen our understanding of the complex, violent, and varied processes that occur in the universe. We learn more about the life cycles of pulsars, the behavior of cosmic rays, and the dynamics of galactic centers. The path forward, therefore, is one of simultaneous refinement and exploration. On one hand, we need next-generation observatories to study these anomalies with unprecedented precision. Radio telescopes like the Square Kilometre Array will detect countless fast radio bursts, allowing us to categorize them with immense detail and potentially find the statistical outlier that points to an exotic origin. Cosmic ray observatories with larger collection areas will gather more of the elusive ultra-high-energy particles, improving our ability to trace their paths back through the magnetic fields of the universe. On the other hand, we need to continue developing our theoretical models of dark matter to predict clearer, more unique observational signatures. Instead of just asking if dark matter could explain a certain signal, we must ask what kind of signal would be impossible to explain without it. The goal is to find a signature that is unmistakable, a fingerprint that cannot be forged by any known astrophysical object. This could be a specific pattern of radiation across multiple wavelengths emanating from a dark, massive object, or a particle detected on Earth with an energy and direction that points directly to the heart of our galaxy's dark matter halo. The search for dark matter within unexplained phenomena is a testament to scientific creativity, a reminder that the answer to our greatest cosmic mystery might not come from looking directly at the dark, but from deciphering the strange flickers of light that dance at the edge of our understanding. The profound mystery of dark matter does not exist in a vacuum. It is woven into the very fabric of fundamental physics, connected by invisible threads to other great cosmic puzzles. Our 23rd mystery asks whether dark matter might be the key that unlocks not just one, but several of the universe's deepest secrets simultaneously. Could the identity of this invisible substance be tied to the origins of matter itself, to the bafflingly small masses of ghostly neutrinos, or even to the universe's explosive birth in inflation? Theoretical physicists are increasingly convinced that the solution will not be a simple, isolated particle, but rather a gateway into a richer, more complete theory of reality. Consider the puzzle of baryogenesis, the question of why the universe is made of matter at all. Our best theories suggest that the Big Bang should have created equal amounts of matter and antimatter, which would have subsequently annihilated each other, leaving behind a universe filled with nothing but light. The fact that we exist is proof that a tiny asymmetry favored matter over antimatter, about one extra matter particle for every 10 billion matter-antimatter pairs. But what caused this imbalance? Intriguingly, the conditions required to produce this asymmetry often involve new particles and forces that operate at extremely high energies, a domain that overlaps significantly with the theoretical territory of dark matter candidates. For instance, some models propose that in the very early universe, interactions involving heavy, hypothetical particles that are their own antiparticles could have simultaneously generated both the matter-antimatter asymmetry and produced a stable relic that we now know as dark matter. In this elegant scenario, the very existence of the atoms that build our world and the invisible halos that bind our galaxies would be two sides of the same cosmic coin, arising from a single primordial process. This leads us directly to the most ambitious frameworks that seek to unify the forces of nature. Supersymmetry, a beloved idea for decades, proposes that every known particle has a more massive superpartner. This theory was originally developed to solve a technical problem with the Higgs boson's mass, but it beautifully provides a perfect dark matter candidate, the lightest supersymmetric particle. If it exists, this particle would be stable, neutral, and would interact only weakly, ticking all the boxes for a WIMP. But the appeal of supersymmetry is its power to solve multiple problems at once. It could stabilize the Higgs mass, offer a path toward unifying the fundamental forces, provide a dark matter particle, and even offer insights into the hierarchy of particle masses. Similarly, theories involving extra dimensions of space propose that gravity appears weak to us because it is diluted across these unseen dimensions. In such models, dark matter could be a particle that is also allowed to propagate in these higher dimensional realms, or it could be a vibrational mode of the higher dimensional fabric itself, a so-called Kaluza-Klein particle. Finding dark matter would not just identify a missing component of the universe, it would be the first experimental evidence for these stunning theoretical extensions of our reality, validating concepts that have, until now, existed purely in the realm of mathematics. Even the bizarre properties of the neutrinos we already know might be connected to the dark sector. Neutrinos are endlessly fascinating. They have tiny, non-zero masses, but the mechanism that gives them this mass remains unknown. The most compelling explanation is the seesaw mechanism, which involves the existence of incredibly heavy, sterile neutrinos that we have yet to detect. These heavy relatives could have been produced in abundance in the early universe, and if they are stable, could constitute the dark matter. Furthermore, the same physics that gives neutrinos their mass could also be linked to the asymmetry between matter and antimatter, potentially tying together three great mysteries: neutrino mass, baryogenesis, and dark matter into one neat package. The invisible world of the neutrino and the invisible world of dark matter may be part of the same hidden family. Perhaps the most profound connection stretches back to the very beginning of everything, the epoch of cosmic inflation. This was the period of exponential expansion, a fraction of a second after the Big Bang, that set the initial conditions for the entire universe. The quantum fluctuations that were stretched to cosmic size during inflation became the seeds for all future structure, including the dark matter distribution. But what if dark matter itself was created during inflation? Some models suggest that dark matter could be a type of particle known as an inflaton, the field that drove the inflationary expansion itself. In other models, dark matter is a byproduct of the inflationary process. If this is true, then by studying the distribution of dark matter in the cosmos today, we are essentially reading a fossil record of the physics that operated at energies 1 trillion times higher than what the Large Hadron Collider can probe. The pattern of the cosmic web, with its specific texture of filaments and voids, could encode information about the nature of inflation, linking the largest structures we can observe directly to the smallest, earliest moments of time. The pursuit of dark matter, therefore, is far more than a cosmic scavenger hunt. It is a central pillar in a much larger architectural plan for fundamental physics. Solving this one mystery could provide the Rosetta Stone that allows us to translate between other seemingly unrelated enigmas. It could reveal why there is something rather than nothing, why the forces have the strengths they do, and what truly happened in the universe's first fleeting instants. The identity of dark matter is likely not a standalone answer, but the first chapter in a much deeper story about the interconnectedness of the cosmos, a story where the darkness holds the key to illuminating everything. Stepping back from the telescopes and particle detectors, we arrive at perhaps the most humbling mystery of all. The saga of dark matter is not merely a scientific puzzle. It is a profound philosophical event, a cosmic revelation that fundamentally challenges our understanding of reality and our place within it. For centuries, our view of the universe was centered on what we could see and touch. We and the world around us were made of atoms, and we naturally assumed that the rest of the cosmos was built from the same stuff. This atom-centric or barycentric view was a form of cosmic narcissism, a quiet assumption that the universe was composed primarily of the same matter that constitutes us. The discovery that over 85% of matter is something entirely different, something that does not interact with light or form the familiar structures of planets and life, is a monumental correction. It tells us in no uncertain terms that the universe is not made for us. The visible cosmos, the pageant of stars and galaxies we have marveled at for millennia, is just the visible frosting on a cake whose substance and bulk are made of something completely alien and unknown. We are not the central characters in the cosmic story. We are fleeting inhabitants of a thin, luminous veneer spread across a hidden architecture whose true nature remains a secret. This realization forces us to confront the limits of our own perception. Our entire existence is mediated by the electromagnetic force. We see with light, we feel the electromagnetic repulsion between atoms. Our technology is built upon it. Dark matter, by its very definition, ignores this force. It is a reminder that our senses and our instruments are tuned to only a narrow slice of the full spectrum of reality. We are like beings who can only perceive the world through sound, living in a universe filled with objects that are completely silent. We would deduce the existence of those objects only when they bumped into something we could hear, just as we deduce dark matter only through its gravitational bumps. The predominance of this invisible substance suggests that what we call reality is merely the fraction of the cosmos that is accessible to our particular biological and technological apparatus. The true nature of the universe may be vastly richer and more complex, with entire layers of existence that are, for now, permanently beyond our direct experience. Dark matter is a testament to the fact that the universe is under no obligation to be fully comprehensible to the human mind. This leads to a deep epistemological question. Does dark matter represent a fundamental boundary to what we can ever know? Or is it simply a temporary frontier, one that will eventually yield to our ingenuity? On one hand, the sheer elusiveness of dark matter, its refusal to be detected despite decades of increasingly sophisticated searches, could be interpreted as a sign that we are bumping against a fundamental limit of observation. Perhaps the dark sector operates on principles so foreign to our own that its components will forever remain hidden, their properties only indirectly inferred through their gravitational shadow. This would mean that a complete theory of the universe might be forever beyond our grasp, a sobering thought for a species driven by curiosity. Yet, the entire history of science is a story of overcoming such apparent limits. We learn to see the electromagnetic spectrum beyond visible light, from radio waves to gamma rays. We discovered the atomic and subatomic worlds, realms utterly alien to everyday experience. Each breakthrough required us to abandon common sense intuition and develop new conceptual frameworks. The mystery of dark matter may be the next great invitation to do just that, to move beyond a physics based solely on the properties of the matter we know, and to develop a new, more expansive understanding that encompasses the dark majority of the cosmos. The challenge is not necessarily a wall, but a door, albeit one that requires a key we have not yet forged. The philosophical implications extend to the very nature of scientific progress. The dark matter puzzle is a powerful example of how science operates at the frontier. It begins with an anomaly: stars moving too fast, light bending too much, that cannot be explained by existing theories. The scientific community then proposes a new entity, a hypothetical substance, to resolve the contradiction. For decades, this hypothesis is tested, refined, and confronted with new data. The current situation, where the simplest versions of the theory are challenged by small-scale observations and direct detection efforts have come up empty, is not a sign of failure. It is the sound of the scientific process grinding forward. It is a period of creative tension where alternative ideas like modified gravity are sharpened against the whetstone of evidence, and the properties of dark matter itself are probed with ever greater precision. This journey reminds us that science does not proceed in a straight line from ignorance to enlightenment. It is a messy, iterative, and often frustrating dialogue between theory and observation. A dialogue that reveals as much about the resilience of the human intellect as it does about the secrets of the cosmos. Ultimately, the story of dark matter is a lesson in cosmic humility. It dethrones us from a privileged position in the material universe, yet simultaneously it is a testament to our audacity. That a species on a small planet, using tools of its own creation, can not only deduce the existence of a reality completely invisible to it, but can also map its distribution across billions of light years and debate its fundamental nature, is a staggering achievement. The darkness we are trying to illuminate is not just out there in space, it is also a measure of the limits of our current knowledge. But in peering into that darkness, we are not just looking for particles. We are searching for a deeper truth about the architecture of existence, and in the process we are discovering a more honest, more wondrous, and far more mysterious place than we ever imagined. The quest to understand dark matter is therefore more than physics. It is a fundamental part of the human project to find our bearing in a vast and enigmatic universe. We have traced the story of the cosmic dark matter web from its quantum origins in the first moments of time to its role in sculpting the galaxies we see today. But this grand narrative is far from over. To complete our journey, we must project our vision forward, not just billions, but trillions of years into the future, to contemplate the ultimate fate of this invisible architecture. The forces that built the cosmic web are still at work, and their long-term battle will dictate the final chapter of the universe's story, a chapter written primarily in the dark. The key player in this distant future is no longer dark matter, the great builder, but its counterpoint, dark energy, the great divider. As the expansion of the universe continues to accelerate, the very fabric of space itself is stretching at an ever-increasing rate. This has a profound and somber implication for the cosmic web. While the dark matter halos that bind individual galaxies and clusters are strong enough to resist this cosmic pull, these structures are gravitationally bound and will remain intact. The larger connections between them are not. The delicate filaments of the web, those vast rivers of dark matter that connect galaxy clusters across the immense voids, are being stretched to their breaking point. Imagine a network of cities connected by long, fragile bridges. As the landscape between them expands, the bridges become taut, then strained, and finally they snap. Trillions of years from now, this is the fate awaiting the cosmic web. Each galaxy cluster, each node of the web will become an isolated island universe. The light from any cluster outside our own local group will be redshifted into complete invisibility, their photons stretched to wavelengths longer than the observable universe itself. The sky, which we see today as a tapestry of galaxies, will go dark for any future astronomers, leaving behind only the stars of their own gravitationally bound cluster adrift in an infinite black sea. This isolation raises a fascinating question about the dark matter within these stranded clusters. Could its distribution evolve over these almost unimaginable timescales? In a stable, isolated cluster, the dark matter particles are in a kind of gravitational dance, orbiting the common center of mass. Over incredibly long periods, a process known as gravitational relaxation could occur. Through subtle gravitational interactions, some particles would gain energy and move to wider orbits, while others would lose energy and sink closer to the core. This could lead to a phenomenon called core collapse in the densest regions, where the central concentration of dark matter becomes even more extreme, potentially forming a massive black hole at the very heart of the dark matter halo. Alternatively, if dark matter has any capacity for self-interaction, no matter how faint, these trillions of years of slow, cumulative collisions could cause the halo to gradually puff up, evolving into a more smooth and homogeneous sphere. The ultimate structure of a dark matter halo may not be static but could represent a balance between gravitational collapse and internal particle dynamics, a balance that shifts over cosmic eons. This leads to the most profound speculative question of all. Could dark matter itself be unstable? Our current models treat it as perfectly stable, a relic that will endure forever. But what if, over these inconceivable time frames, dark matter particles can decay? Much like a radioactive element with an immensely long half-life, a dark matter particle might spontaneously transform into lighter, more familiar particles. If this decay were to occur, it would fundamentally alter the universe on the most basic level. The invisible gravitational glue holding galaxies and clusters together would slowly weaken. As dark matter decayed away, its gravitational influence would diminish. The outer stars in galaxies would begin to drift off into the void, and eventually, even the clusters themselves would dissolve. The universe would transition from a state of structure to a state of ultimate emptiness, a thin, ever-expanding soup of elementary particles and radiation. The cosmic web would not just be severed, it would vanish entirely. Conversely, a different transformation might be possible. Some theories suggest that the properties of dark energy could be tied to the density of dark matter. In such a model, as the universe expands and the dark matter density drops, the nature of dark energy itself could change. Perhaps the repulsive force could weaken or even reverse sign, becoming attractive once more. This could potentially halt the acceleration and initiate a new cycle of contraction, a big crunch. In this scenario, the fate of the cosmic web would be one of dramatic reunion. The isolated clusters would begin to fall back toward each other, the filaments reforming as the universe collapses in on itself. The dark matter web would act as a cosmic memory, guiding the universe back to a hot, dense state, potentially setting the stage for a new Big Bang. While this cyclical model is highly speculative, it illustrates that the ultimate fate of the dark matter web is inextricably linked to the still mysterious nature of dark energy. Contemplating these distant futures is more than a theoretical exercise. It is a profound meditation on the nature of existence. The cosmic dark matter web, for all its current dominance, is not necessarily a permanent feature of the cosmos. It had a beginning, and it may well have an end. Its story is a testament to the dynamic and evolving nature of the universe, a realm where even the most fundamental structures are subject to change over deep time. Our ability to peer back to the beginning of the web and project forward to its possible demise is a remarkable achievement of human curiosity and intellect. It connects our fleeting moment of consciousness to the grandest scales of time and space, reminding us that we are witnesses to a single, beautiful frame in a cosmic movie that is still playing out. The mystery of its ultimate fate ensures that the story of the dark universe will continue to captivate and inspire for as long as we look to the sky and wonder what lies in the dark. And so our journey through the 25 mysteries of the cosmic dark matter web comes to a close. We began by asking how we can be so sure of something we cannot see, tracing the gravitational evidence from the unexpected spin of galaxies to the profound bending of light. We wrestled with the fundamental identity of this invisible substance, from the heavy WIMP to the wave-like axions, and confronted the puzzles it presents within our own galactic backyard: the missing satellites, the core cusp problem, and the too-big-to-fail paradox. We scaled the immense architecture of the cosmic web itself, marveling at its filaments and nodes, and then faced the cosmic crisis of the Hubble tension, a disagreement over the universe's expansion that may point to deeper physics in the dark sector. We traveled back to the cosmic dark ages, where dark matter laid the foundation for the first stars, and then grappled with the bizarre existence of galaxies seemingly devoid of this very substance. We explored the high-stakes hunt for dark matter, from the silent laboratories buried deep underground to the scans of the galactic center for signs of annihilation. We saw how computer simulations recreate the universe's evolution, and how alternative ideas like modified gravity are tested and challenged by the brutal evidence of colliding galaxy clusters. We pondered the influence of black holes and the pristine information locked in the cosmic microwave background, and we considered the ultimate cosmic struggle between the gravitational pull of dark matter and the repulsive push of dark energy. We even ventured into the quantum realm, where dark matter might behave as a galactic-scale superfluid, and we asked the profound question of what it all means for us, for life, and for our very place in a cosmos dominated by the unseen. We look to the future, to the next generation of telescopes and detectors that will push the search into new frontiers, and we connected the dots to other great mysteries of physics, from the matter-antimatter asymmetry to the possibility of extra dimensions. We confronted the philosophical shock that most of the universe is made of something fundamentally alien to our experience, and we projected our vision trillions of years into the future to contemplate the ultimate fate of the cosmic web in an accelerating universe. Each of these 25 mysteries is not a dead end but a frontier. They represent the very cutting edge of our understanding, the places where our knowledge ends and discovery begins. The progress we have made is nothing short of breathtaking, from a mere anomaly in galactic rotation to a detailed map of an invisible universe that governs the fate of all we see. We have moved from suspecting the dark to charting its architecture, yet for every question answered, new and deeper questions have emerged. The absence of a direct detection, the strange behavior of dark matter in clusters like Abell 520, the lingering tension in the Hubble constant, these are not failures but guides. They are the cosmos telling us that the dark sector is richer and more complex than we ever imagined. This ongoing quest is a powerful testament to human curiosity and ingenuity. It is a story that reminds us that the universe is under no obligation to be simple or easily understood. the greatest discoveries often lie not in the light, but in the shadows, in the anomalies that challenge our most cherished assumptions. To solve the mystery of dark matter is to do more than just identify a particle. It is to unlock a deeper layer of reality. It could reveal new forces and particles, rewrite the story of the universe's birth, and finally explain why the cosmos is structured the way it is. It would be a revolution on par with understanding that the Earth revolves around the Sun, forever altering our perspective. So, as new data streams in from the Vera Rubin Observatory and the James Webb Space Telescope, as deeper underground labs switch on and more powerful colliders are planned, keep looking up and wondering. The next great breakthrough could be just around the corner, waiting to be pieced together by a curious mind. The dark universe has kept its secrets for billions of years, but the light of inquiry is shining ever brighter into the shadows. The story is not over. In many ways, it has only just begun.